Hello everyone, how are you all doing tonight? Oh, I clicked there they are, that. Aravera, thank you very much for the BWOPs. Yeah, hello Blossomy Lamb, good to see you, how are you doing? Yeah, hope you're having a good time, hope you're doing great. Tonight is gonna be the finale of, like, my series of learning Rust on stream. I am very excited. It's gonna be really cool. Yeah, like, I've got 2 chapters left and I am so excited. Gonna be fun. But yeah, there been, like, anything interesting I've been doing recently? Oh, yeah, I did try. Yeah, I gave playing Horizon Zero Dawn a shot last night, and it just turned out like the watchers in that game give off just this piercing whine, which just causes me physical pain, so I had to, like, just stop. So yeah, oh well. Ooh, more BWOPs, thank you, Era. Yeah, tonight I have 2 chapters of the Rust book left. I've got the advanced features, like unsafe, advanced traits and types, functions, closures, and macros, and I've got the final project, and we're going to be getting through those. I'm super excited, I cannot wait. So, without further ado, how about we get going? Oh yeah, have you ever played Subnautica or Risk of Rain 2? They're both very good. Yeah, I've got Subnautica, I've played, like, some of it, I haven't gone super far. I do want to play Risk of Rain 2 sometime. That sounds like it'd be really fun. Yo! While I'm still getting, like, my sources set up. Hello, Jasper. Hello, Ziona. Yeah. How are you, too? Ooh, Master Chief Collection? Barmaid Raid, hello. Let's... Yeah, in Master Chief Collection, hope you two are having a great time. How was it? Now let me quickly pull up a thing. There. Beep, beep. Let's go. Sorry if I sound like sniffly tonight. My allergies have been hella acting up. It blows. Yeah, very rough 4 hours fun. Now, hello, Non. Great to see ya. Yeah, my allergies have been acting up last couple days. Been taking meds for them, so hopefully they won't be super bad tonight, but yeah. Good seeing you, yeah, So, by now you've learned the most commonly used parts of the Rust programming language. Before we do one more project in Chapter 20, we'll look at a few aspects of the language you might run into every once in a while. You can use this chapter as a reference for when you encounter any unknowns when using Rust. The features you'll learn to use in this chapter are useful in very specific situations. Although you might not reach for them often, we want to make sure you have a grasp of all the features Rust has to offer. In this chapter, we'll cover unsafe Rust, how to opt out of some of Rust's guarantees and take responsibility for manually upholding them. Advanced traits, associated types, default type parameters, fully qualified syntax, super traits, and the new type pattern in relation to traits. Advanced types, learn more about the new type pattern, type aliases, the never type, and dynamically sized types. Advanced closures and functions, including function pointers and returning closures. And macros, ways to define code that defines more code at compile time. It's a panoply of Rust features with something for everyone. So let's dive in. All the code we've discussed so far has had Rust memory safety guarantees enforced at compile time. However, Rust has a second language hidden inside of it that doesn't enforce these memory safety guarantees. It's called unsafe Rust. And it works just like regular Rust, but gives us extra superpowers. Unsafe Rust exists because, by nature, static analysis is conservative. When the compiler tries to determine whether or not code upholds the guarantees, it's better for it to reject some valid programs than to accept some invalid programs. Although the code might be okay, if the Rust compiler doesn't have enough information to be confident, it'll reject the code. In these cases, you can use unsafe code to tell the compiler, trust me, I know what I'm doing. Downside is that you use it at your own risk. If you use unsafe code incorrectly, problems due to memory unsafety such as a null point or deref can occur. Another reason Rust is an unsafe alter ego is that underlying computer hardware is inherently unsafe. Rust didn't let you do unsafe ops, you couldn't do certain tasks. Rust needs to allow you to do low-level systems programming, such as directly interfacing with the OS or even writing your own OS. Working with low-level systems programming is one of the goals of the language. Let's explore what we can do with unsafe Rust and how to do it. Alright, so it's time for the danger zone. To switch to unsafe Rust, you use the unsafe keyword and then start a new block that holds the unsafe code. You can take 5 actions in unsafe Rust called unsafe superpowers that you can't in safe Rust. Those powers include the ability to dereference a raw pointer, call an unsafe function or method, access or modify a mutable static var, implement an unsafe trait, or access fields of unions. It is important to understand that unsafe doesn't turn off the borrow checker or disable any other of Rust's safety checks. If you use a reference in unsafe code, it will still be checked. The unsafe keyword only gives you access to these 5 features that are then not checked by the compiler for memory safety. You still get some degree of safety inside an unsafe block. In addition, unsafe does not mean that the code inside the block is necessarily dangerous or that it will definitely have memory safety problems. The intent is that as the programmer, you'll ensure that the code inside an unsafe block will access memory in an invalid way. It's like a kitchen knife. Yeah, you can get cut with it if you don't know what you're doing, but if you're careful, you can do way ton more with it that you just can't otherwise. People are fallible and mistakes will happen, but by requiring these 5 unsafe operations to be inside blocks annotated with unsafe, you'll know that any errors related to memory safety must be within an unsafe block. Keep unsafe blocks small. You'll be thankful later when you investigate memory bugs. To isolate unsafe code as much as possible, it's best to enclose unsafe code within a safe abstraction and provide a safe API, which we'll discuss later in the chapter when we examine unsafe functions and methods. Parts of the standard lib are implemented as safe abstractions over unsafe code that's been audited. Wrapping unsafe code in a safe abstraction prevents uses of unsafe from leaking out into all the places that you or your users might want to use the functionality implemented with unsafe code because safe abstraction is safe. Let's look at each of the 5 unsafe superpowers in turn. We'll also look at some abstractions that provide a safe interface to unsafe code. Alright, before we do that, I do want to note, like, a new version of Rust just dropped yesterday, and there's some cool stuff in it. Cool things in 159.0 stable. We got inline assembly, so if you're targeting x86-64, you can just write raw ASM in. This does require, this is unsafe because you are just directly writing, you are directly writing machine code, so like, that is a new unsafe superpowers. Just write the machine code yourself. Hello, Maddie Makes Games, great to see ya. Yep, today the stable Rust compiler supports inline assembly on x86 and x86-64, ARM, AArch64, and RISC-V. I would really, it would be so cool to have like ASM support for like WASM or such. That'd be cool. Alright. Then we've also got destructuring assignments. You can now use tuple, slice, and struct patterns as the left-hand side of an assignment. That means that, like with let statements, you can now like do tuple destructuring into existing variables. You can, like, all this destructuring stuff, structs, arrays, tuples, all that jazz. It'll make, I was really surprised that ASM wasn't stable yet. In most cases, though, user probably already used other unstable features, Then, other good things. Const, generics, defaults, and interleaving. Generic types can specify default values for their const generics, so like const nu size equals 2 or such, Yep. Previously, type params were required to come before all const parameters. That restriction has been relaxed and you can now interleave them. Neat. Future incompatibility warnings. So there's some stuff like, Yep. Borrows of packed struct fields was being allowed in safe code, which it should not have been. Yep. Can be quite disruptive when a crate used by your project has code that'll no longer be allowed. Yep, so now during a cargo build or check, you'll note that, okay. I was really surprised destruction didn't already exist. I only ever used destructuring on Tuple, so I didn't really use it, yeah. Improvements to constant generics are always nice, found them to be pretty nice. Now, yeah, then there's also stripped binaries, so you can strip out debug info or symbols or such. Keep symbols in, it makes decompilation a lot easier. Yeah, and right now, because of bug number 94124, which is an internal compiler exception indexed out of bounds, they've turned incremental compilation off by default for now. This will be turned back on as soon as it's fixed, but they just want to like make sure it is fixed. Yeah. A lot of stabilized APIs, so available parallelism, result copied and cloned, ASM, yep. Scroll flow is breaking, continue, trifum car for U8, car trifum car error, implementing clone debug display, partial light copy and error. Yep. Iter zip is now safe, hell yeah. Is power of 2 on non-zero U8, U16, U32, U64, U128. Double-ended iterator for to lowercase and to uppercase. Trifum and mute T for array T 7:n. Unwind safe for once and ref unwind safe for once. Yep. And previously stable functions are now const. Nice. All right. Cool. Very nice. Second, let me let me know. God, I hate allergies. Alright, so, yeah. I'm not gonna update Rust right now just because, like, the book isn't gonna use any of those, but I will at some point later, but yeah. In Chapter 4, in the Dangling References section, we mentioned that the compiler ensures references are always valid. Unsafe Rust has 2 new types called raw pointers that are similar to references. I'm surprised iter zip was unstable and exists because it seemed to be just special wraparound iterator zip, yeah. Wiggle because that's unnecessary and unsafe, yeah, it's not doing anything. Yeah. So, compiler ensures references are always valid. Unsafe Rust has 2 new types called raw pointers that are similar to refs. Yep, they are written as *const t and *mute t. Alright, asterisk isn't the deref operator, it's part of the type name. Context of raw pointers, immutable means that the pointer can't be directly assigned to after being derefed. Yeah, these are just like raw pointers, yep. Raw pointers are allowed to ignore borrowing rules by having both immutable and mutable pointers or multiple mutable pointers to the same location, are not guaranteed to point to valid memory, are allowed to be null, and don't implement any automatic cleanup. By opting out of having Rust enforce these, you can give up guaranteed safety in exchange for greater performance or the ability to interface with another language or hardware where Rust guarantees don't apply. So, inside our unsafe, we can let mute num equals 5 and let r1 equals pointer num as *const i32. Then, yep, so that's a pointer to const i32, yep, which is immutable. And let r2 equals and num as, let mute, yep, and mute num, yeah. Mute num as mute i32. There. Yeah, yeah, these are now legal in this unsafe block. unused, so like still an unnecessary unsafe, but yeah. We don't include unsafe in this code. We can create raw pointers in safe code, we just can't deref them outside of an unsafe block. Created raw pointers by using as to cast to an immutable and immutable reference into their corresponding raw pointer types. Since we created them directly from references guaranteed to be valid, we know these particular raw pointers are valid, but we can't make that assumption about just any raw pointer. So now let's say, like, let add address equals x012345 use size. Let r equals address as const I32. There. Yeah. Yep. Usually there's no good reason to write code like this, but it is possible, yep. Sniffly Yeah. We can create raw pointers in safe code, but we can't deref raw pointers and read the data being point to. We use the deref. Right, so now we can start doing stuff that's unsafe. Yeah, let's just, actually, let's clean this up quick, but yeah. Useful when we're trying to write code for the TI-84, yeah. So, let mute num equals 5. Let r1 equals num as const I32. Let r2 equals and mute num as mute I32. And in unsafe, println r1 is deref r1 and println r2 is r2 run. Yay. I wonder if anyone's gotten Rust working for the 6. I wonder, yeah. Right, 6502 isn't great for compilers anyway, F. Oh, they have, yeah. Yeah, like, folks have, just like it's not super compiler friendly. Yeah. Okay. Recall that we can create raw pointers in safe code, but we can't deref raw pointers and read the data being pointed to. In listing 19.3, we use the deref on a raw pointer that requires an unsafe block. Yep. Creating a pointer does no harm. It's only when we try to access the value that it points to that we might end up dealing with something illegal. We created starconst I32 and starview I32 raw pointers that both pointed to the same memory location where num is stored. But yeah, if we tried to create a mutable and immutable ref, then it would have just not compiled because that's ownership violation. Someone made an LMVM target for something, you can write Rust for it. Now the ability to compile it easily or standard core or alloc are not guaranteed, yeah. Oh no, that gives me a horrible idea. Oh, that gives me a horrible idea! Oh no. Yeah, You're like, is there an... Yep, there is an LLVM Z80. Woo! Oh god, yeah. Not Jacobio's fork. Oh boy. Not good, or... Yeah, crashes VS Code when I try to merge the Rust LLVM fork with it. Oh no! I would love to write Rust code for something just cursed. Yeah, yep. Calling an unsafe function method. Second type of operation that requires an unsafe block is calls to unsafe functions. Unsafe functions and methods look exactly like regular functions and method, but they have an extra unsafe before the rest of the def. Unsafe keyword in this context indicates the function is requirements we need to uphold when we call the function. Rust can't guarantee we've met them yet. Oh. Yep. Actually really good. Used in the C tool chain for TI-84. Ah, okay. I love when the app I use to make sure my computer doesn't fall asleep crashes. Yep, like, let's say unsafe and dangerous. And we can call dangerous in here, yep. Let's call it within a separate unsafe block. Otherwise, we'll get an error. Ah. By inserting the unsafe block around our call to dangerous, we're asserting to Rust that we've read the function's doc, we understand how to use it properly, and we verify that we're fulfilling the contract of the function. Bodies of unsafe functions are effectively unsafe blocks, so to perform other unsafe ops, we don't need to add another unsafe block inside. Okay. Main issues are 1, Rust has a custom LLVM fork, and 2, the EZ80 has 24-bit pointers. Oh god. Fun. Yeah, that's a fun U size. Alright. Yep. Just function contains unsafe doesn't mean you need to make the entire function. Yep. Wrapping unsafe code in safe function is pretty common. Yep. That function from standard lib split mute. Yeah. Yeah. Require some unsafe code and explore how we might implement. Okay. So let's just let mute equals deck 1 2 3 4 5 6. Then let r and mute let a b r split at Oh god, that was an explosive sneeze. Assert ec a and mute 1 2 3. Assert. Nope. Assert ec b and 6. Yeah, this should be fine. So run it. Shouldn't be any issues. Oh, why are you there? What was that, like, intrinsics are likely to never be stabilized about? Is that, like, just, what are... they're LVM stuff, it looks okay, yeah. Yep. Provide operations intended to act on I/O memory, which are guaranteed not be reordered by the compiler across other... Okay, so... I'm guessing this is like... Yep. This is like internal LVM stuff. Okay, got it. So can't implement using only safe rest. That might look something like this. So, then split at mute slice nice and mute I32 mid size and mute I32 and mute I32 and let len equals slice len assert mid less than equal len and mute slice dot mid and mute slice mid dot semicolon. That's illegal because that is two mutable borrows at once. So we would unsafe. Yeah, so. Yep, so instead we're gonna just. Right. Yep. Can't understand we're borrowing different parts of the slice, only knows we're borrowing from the same slice twice. Borrowing different parts of a slice is fundamentally okay because two slices aren't overlapping, but Rust isn't smart enough to know that, and it'd be like a pain in the ass to like do the heuristic. So just like make a function for it that uses unsafe and just make sure it's safe because we know it's safe. So yep. This means yep. Yeah, so we're gonna have a let pointer will slice as mute. Yep. Then return slice from raw parts mute pointer mid and slice from raw parts mute pointer and mid len minus mid. Yeah. This is legal. Oh, yep. Use standard slice. There. Yep. Oh! Oh, that's interesting. Oh, that's smart compiler. Oh, smart compiler! Ooh! I just realized that we have a use name from standard slice and a parameter name, and Rust knows which one it should be using here. Neat! That's cool. Yeah. Yep, recall that slices are a pointer to some data and the length of the slice, yep. Use len to get, yep, so, from raw parts mode is unsafe just because you've got to make sure that you're not like creating a double ref. Yep, safety, the caller must uphold the safety contract for raw parts mute. Yep. Yeah. Yep. So pointer safety is non-null dangling, yep. So just don't make things dangling, yep. Behavior is undefined if any of the following conditions are violated. Data must be valid for both reads and writes, yep. And it must be properly aligned. Our memory range of this slice must be contained within a single allocated object. Slices can never span across multiple allocated objects. Data must be non-null and aligned even for zero-length slices. Yep. One reason is enum layout optimizations may rely on refs, including slices of any length being aligned and non-null to distinguish them from other data. You can obtain a pointer that's usable as data for zero-length slices using non-null dangling. Neat. Data must point to length, consecutive property, initialized values of type T. Yep. Alright, neat. So yay. Yeah, basically, we're making sure that, like all unsafe is we're saying, hey, push that complexity onto me, the user. I can handle it. I know what I'm doing. Yeah, I think that is, like, just something that, like, is not really talked about enough with, like, programming, just generally, like, a lot of, like, computers are complex. They are unimaginably complex. Like, do you know how long it has been since since it has been, like, at all feasible for one person to perfectly understand what every single part of a computer is doing? I'm pretty sure, like, yeah, Moore's Law, I'm pretty sure this has, like, is this, no, I know there's, like, a list of, like, transistor counts over time somewhere on Wikipedia. I don't remember where it is, but yeah. Yeah, like, basically, oh, here's, like, a good chart, yeah. Like, just, look, back down here at the Intel 4004, that still has, like, well over, like, 2,500 transistors, yeah. We've gone from people being able to write ASM, pretty much direct CPU calls, to needing high-level languages to do anything more than toys. I mean, like, not even that, like, like, you can, like, theoretically, like, write ASM, like, x86 ASM web serve. Like, there was, I remember recently, yeah, ASM TTPD was, like, a thing that made headlines recently. It is a web server for Linux written in in AMD 64 assembly. Like, it is all in ASM. All of it is just... This is it. It is written in assembly, yeah. It's still pretty simple to make important things in ASM, yeah. Just like, what I'm saying is, like, you can absolutely still write things in assembly, but assembly is an abstraction. It's all abstractions, all the way down. Abstractions on abstractions on abstractions on nothing. Like, there's just so much that goes into a computer, just back, like, with, like, the Intel 4004, 8008, or, like, the Z80, or, yeah, or, like, the 6502, you could look at a chart for a few, like, you could, like, memorize a chart and, like, figure out what every single transistor in that machine is doing. You could then make a version of the board where every single transistor is a discrete transistor. Oh, audio. Yeah, like, you could make a monster 6502. That is not a problem. Like, this is a thing that it would take a lot of time, it would take a lot of work, but it would be possible. This is absolutely, like, a real thing. It was I saw it at Maker Faire 2016. Like, it was really fucking cool. Why is my... Snip, are you good? I think Snip... I might need to update Snip. My now playing view isn't working. Oh well, yeah, it might be something with new OBS. Yeah, I'll figure it out, but yeah. Yeah, like, you can make a Monster 6502. You can make, like, a machine, like, you can make a discrete version of a 6502. Like, yeah, like, you cannot make a discrete version of, like, an Intel Xeon, or an Apple M1, or an A13, or a Ryzen 7. You cannot make a discrete, like, modern chip. There is so much knowledge there that is fundamentally impossible to, like, it is at a fundamental level impossible for one person to understand perfectly any chip. You have to go through abstractions. You have to go through gates, or, yeah, logic units or stuff. And you can't make a discrete Pentium. Exactly, yeah. It has been decades since, like, we left the era of understandability. Like, yeah, like, it is just, like, we are building things, like, computers are something we fundamentally do not and cannot perfectly understand in the way that you could perfectly understand, like, a mechanical machine. Like, it's just not possible. Like, once you get, like, to the 8086, that's, like, got tens of thousands of transistors. That is almost impossible to perfectly understand. Like, you can understand the units, the logic gates. Hell, like, you can recreate the logic gates, you can emulate them, you can make something cycle accurate. But you can't understand it the way you could understand a 6502 or an 8008. Ada, shut up. I love you. Yeah, like, that is just a really... It's just something that is really interesting to think about, of, like, how much of everything is abstraction. It's just really, really interesting. Yeah. Yeah, like, slice your pointer to some data, yep, len to, yep, as-mute pointer to access raw pointer, yep. As-mute pointer returns raw pointer with the type mute I32 to stored in variable pointer, yep. Keep the assertion that mid is within the slice, yep. Then we get to the unsafe code. The slice from raw parts in mute takes a raw pointer and a length and creates a slice. We use this function to create a slice that starts from pointer and is mid items long. Then we call add on pointer with mid to get a raw pointer that starts at mid. Yeah. Oh, I think it's because it's unsafe that you can't, like, just use, like, a plus operator. Yeah. Yeah. Alright. Yeah. Don't need to mark the resulting split at mute function as unsafe, and we can call this function from unsafe rest. We've created a safe abstraction unsafe code with an impl of the function that uses unsafe in a safe way. But because it creates only valid pointers from data the function has access to. That's cool. We don't own the memory at this arbitrary location, and there's no guarantee. Yep, so, yeah, this would be illegal because, like, yeah. Like, just because we don't own this memory, we're just writing a pointer, we're just messing around, like, that's a seg fault. That's, like, this is begging for a seg fault. Yeah. No guarantee that code creates valid I32s, yep. That's UB. And probably a seg fault, yeah. Sometimes you do own that memory, yeah. Exactly, yeah, like, Yeah, like, that's the thing, like, sometimes you do own the memory, and then that is safe, but you need to know and trust that you own the memory. Like, this is still legal Rust code. It's just like, this configuration is Rust code that would crash. Like, as this is, like, if you're just, like, putting in a random address and treating it as an array slice, that won't work. But Rust will still let you compile this, and that's the whole thing with unsafe, is it trusts you to know whether you own the code or not. It is putting that complexity onto you instead of having the complexity in the language. That's like just kind of how it works. Yeah. Yep. Sometimes the Rust code might need to interact with code written in another language. So that's what we've got Extern for. Facilitates creation and use of FFI. Woo! FFI way for programming languages to define functions and enable a different foreign programming language to call them. Yep. 19.8 demonstrates how to set up integration with abs from C standards. So yeah, for example, we can so we can extern C, on abs, input I32 to I32. Then, in unsafe, we can println absolute value of -3 according to C, abs -3. There. That's legal. Yep, that works, yeah. Without the extern C block, we listen, or within the extern C block, we list names and signatures of external functions from another language. Yep. C part defines which ABI the external function uses. ABI defines how to call the function at the assembly level. C ABI is the most common and follows the C ABI, yep. We can also use extern to create an interface that allows other languages to call Rust functions. Instead of an extern block, we add the extern keyword and specify the ABI to use just before the fun keyword, yep. We also need to add a no mangle annotation to tell the Rust compiler to not mangle the name of this function. Mangling is when a compiler changes the name we've given a function to a different name that contains more information for other parts of the compilation progress to consume, but is less human readable. Every programming language compiler mangles names slightly differently, so for a Rust function to be nameable by other languages, we must disable the Rust compiler's name mangling. So yeah. So that means we can go hash no mangle annotation pub extern C fun call from C println just called a Rust function C, and this doesn't require unsafe because it's Rust internal. But yeah, I think that's cool. Accessing or modifying a mutable static variable. Yep. Until now we've not talked about global vars, which Rust does support but can be problematic with ownership rules. If two threads are accessing the same mutable global var, it can cause a data race. Yep. Global vars we call static. Oh. Still to me that you need extern instead of just C fun. Yeah. I mean, I get why, but yeah. Yeah, like, I understand why, just because of, like, the extra annotation, like, helping the compiler, and then, like, the discrimination for, like, which ABI to use, but yeah. Extern C is a holdover from C++. Yeah. Yeah, like, Rust is built on other languages. So, we could static hello world and stir equals hello world. There. Yep, then we can println name is hello world. Okay. Static vars similar to constants, which we discussed in differences between vars and constants, yep. Names of static vars are in screaming snake case by convention. Static variables can only store refs with prime static, which means Rust compiler can figure out the lifetime and weren't required to annotate explicitly, yep. Accessing an immutable static variable is safe. Constant and immutable statics might seem similar, but statics have a fixed address in memory and consts are inlined at compile time. Yep. Certain C and C++ tells the compiler to target the enclosed declarations within the C API and not perform C++ name angling. Yeah. You know, like, Rust is, like, fundamentally built off a lot of different languages that have come before it. Like, let mute is from Swift. The extern stuff is from C++. Yeah. Constants and immutable static vars might seem... Oh, read that, yep. Static variables can be mutable, but this can be a bit weird. So, yeah, but, yeah. Yeah, accessing and modifying mutable statics is unsafe. So, add to count inc 232 unsafe. Let's say like counter 232 counter plus inc, and we can add to count 3 and unsafe until then counter counter and run this. Yay! Yep, specify mutability by using mute. Yep. Any code that reads or writes must be within an unsafe compiles and prints. Yep. Because it's single-threaded, having multiple threads access counter would likely result in data races. Oh no. With mutable data that's globally accessible, it's difficult to ensure there are no data races, which is why Rust considers mutable statics to be unsafe. Preferable to use concurrency techniques and thread-safe smart pointers, yep, so the compiler checks data access is done safely, yeah. Then, another use case for unsafe is implementing an unsafe trait. Trait's unsafe when at least one of its methods has some invariant that the compiler can't verify. Alright. So that'd be like, yeah. Yep. Just mark, yeah, gotta mark both the trait and its impulse as unsafe, yep. That means it's on us to do it. Yep, sync and send, yep. Compile implements these traits automatically if they're composed of send and sync types. If we implement a type that contains a type that is not send or sync, such as raw pointers, and we want to mark it as send or sync, we must use unsafe, and we've got to handle that ourselves. We can't verify our type upholds guarantees that it can be safely sent across threads or accessed from multiple threads. Therefore, we need to do those checks manually and indicate as such. Yep. Yep. Then, lastly is accessing field of a union, which is similar to a struct, but only one declared field is used in a particular instance at one time. Unions are primarily used to interface with unions in C code, just because, like, we've got enums, which kind of do the thing better. Yep. Using unsafe to take one of the 5 superpowers isn't wrong or even frowned upon, but it is trickier to get unsafe code correct because the compiler can't help uphold memory safety. When you have reason to use unsafe, you can do so, and having the explicit unsafe makes it easier to track down the source of problems when they occur. Alright. So yeah, basically, it's a kitchen knife. Just be careful when you're using it. I will have to, like, figure out why, like, snip isn't working, but yeah. Pretty sure I can, like, yeah, I'll have to look sometime, yeah, don't want to get sniped with that. I do want to, like, finish the Rust book tonight, so yeah. So, yep. We didn't discuss more advanced details of traits, so let's get into the nitty-gritty. Okay. Associated types connect a type placeholder with a trait such that the trait method defs can use these placeholder types in their SIGs. Impl of a trait will specify concrete type. Yep, we've seen that with like item in iterator and such. Yeah. Yep. We've described most of the advanced features as being rarely needed. Associated types are somewhere in the middle. Used more rarely than features explained in the rest of the book, but more commonly than many of the other features in this chapter. Yep. Yeah, iterator, item, or stuff like that. Yeah. Or like deref has one. Yeah. Items a placeholder type. Next method's def shows that it'll return the types option self item. Yep. Yeah, basically, just gotta say what that item type is. Might seem similar to generics. Yep. Yeah, so I use ATs. Yep. Yeah, basically just, yeah, Yep, so let's examine difference using two constants with an example. Yep. Impulse iterator on counter struct. Yeah. We learned item was U30, or specified item was U32. Yep. Comparable to generic, so why not just define iterator like this? Yeah, we must, but in, 1913, we must annotate the types in each impl, because we can also implement iterator string for counter or any other type. We would have multiple impls of iterator for counter. Yep. When treated as a generic param, it can be implemented for a type multiple times, changing concrete types of the generic type params each time. Used next, we would have to provide type annotations to indicate which impl of iterator we want to use. So associated types just lets you like tie that a bit tighter because you're specifying one. Yeah. You don't have to specify we want an iterator of U32 values everywhere they call next on counter. Yeah. Alright. Default generic type parameters and operator overloading. When it's generic type parameters, we can specify default concrete type for the generic. Eliminates the need for implementers of the trait to specify a concrete type if the default type works. Yep. So placeholder type equals concrete type. Yeah. Yeah. Cool. Yep. When declaring generic type. Yep. Great example is operator overload and customizing behavior of an operator in particular situations. So, let's do that. So, use standard ops add hash derive debug copy clone partial f struct point x I32 y I32. Then we can impl add for point type output equals point. Then we can fun add self other point to point. Then return a new point x self dot x plus other x y. Alright, it self y plus other dot y. Yeah. So does that just like it's weird. I don't get like when like I don't get what will make Rust Analyzer like choose when to like autofill those parameters. Oh well. Yeah. Is it only when it's like there is. Alright, so I can do that to select it. Okay. Right. Oh, yeah. I guess it's when it's the return type of the function. Got it. And now we can assert x point x1 y0 plus point x2 y3 point x3 y3, and that should be legal. Yay. Yay. Adds the 2x values. Yep. Got no idea what's happening yet. TBH, no. Yeah, I am doing just like, I am very late, like, I'm getting close to, like, the end of this, like, language tutorial book. I'm, like, learning a new programming language, and it's really cool and fun, yeah. Like, I've done a lot of streams of this now. I've been, like, going through this entire book, and I am very close to the end. Yeah. So, yeah. Add adds to x values of point and y values of point, yep. Has an associated type named output, so we just, like, yeah. Default generic type in this code in the add trait, so yeah. So yeah, yep. So that's a default type parameter, so like, this will be like, or, yeah. So like, we can impl add for point, and that'll default to add point. Then we could, like, impl add I32 for point. Then add self other. Then, oh yeah, then I've got a type output equals point I32 to point. So then I could point the x is the self x plus other, then self y plus other. Yeah, there, like that. So then I could assert x point x1 y o plus 32, then point x33 y 32. And something like that'll work. Bip and bip bip bip. Yeah. Yeah. So yeah, that's cool and neat. Okay. Yeah. Yep. Yeah, so that's default RHS, yeah, so now you could do something like this, which is kind of like similar to what I did. So yeah, you can specify what type you want to add, and it'll just default, like, it'll default to that type there. But yeah. Alright, yeah, so we can write this out. Struct millimeters to 32. Struct meters 32. Then impl add meters or millimeters. Type output equals millimeters. Then add self other meters to millimeters self O plus other O times 1000, yep, and something like that. Specify impl add meters, yep. Yeah, to extend a type without breaking existing code and to allow customization in specific cases most users won't need, yeah. Add is an example of the second purpose. Usually I'll add two like types, but then you can add two unlike types, yep. Using a default type parameter in add def means you won't have to specify the extra parameter most of the time. Bit of implementation boilerplate isn't needed, making it easier to use the trait. First purpose is similar to the second, but in reverse. If you want to add a type parameter to an existing trait, you can give a default to allow extension of the functionality of the trait without breaking the existing impl code. Yeah, I am gonna be right back. I just need to go for a second. Yeah, I'll be back in just a minute. back, y'all. Hope y'all are doing good. Okay. Alright, well. Alright. So we did alright. Next up is fully qualified syntax for disambiguation, calling methods with the same name, yeah. Yep. Okay, so let me clear all this up. Alright, so. Create pilot. Fly. And self. And create wizard. And fly. And self. Yep. Then we've got a direct human. Yeah, so this is like pretty, yeah, so like basically this is the whole thing of like, oh god, what if, yeah, like you're gonna have a lot of things with the same name. How do you figure out which one you want to do? Yeah. Yep, you'll need to tell Rust which one you want to use. Yep, so yeah. Then we can impl pilot for human. Fly and self. Println. This is Captain speaking. Then impl wizard for human. Oh, I can just do that. Okay. Println up. Then let's impl human and fly and self. Println. Oh, I love having shaky hands, waving arms furiously. Yep. So we wanted to call fly, yeah. So then, let human equals human, then human fly. Then, oh god, which one does it mean? Yeah. Yep, or this'll just show that, yep, so this one will just call like the one here because it's the one directly on, so yeah. Waving arms seriously, bah. Right, yep, so. Yep. We can also use the function pointer, human, human, and human. So we can do that. Yep. The specifying trait name before the method name clarifies the rest of which impl fly we want to call. Yep. Yeah. Then, yeah. Yeah, because all traits are just fundamentally functions, so just, yeah. Pilot, fly, and wizard, fly, and human. Then, yeah, human.fly. Yeah, and here's the fun thing about that. Then, now you can, for example, let flight equals pilot fly. Then, you can flight human. And human. Not carrot. And. So, all of these should be good, yep. Woohoo! Yeah. Hooray, function pointers! Nice. Yeah. Yep. Okay. Yep. So you just need to be more specific, yep, by passing them. Specifying trait name before method name clarifies to which impl fly we want to call, yep. Also want to, yeah, we could also write this, yeah. This is a bit longer to write if we don't need to disambiguate. This fly takes a self parameter if we had two types that both implement one trait. Rust can figure out which impl of a trait to use based on the type of self. Yay! However, AFs that are part of trait, don't have a self, AFs that are part of traits don't have a self param. When two types in the same scope impl that trait, Rust can't figure out which type you mean unless you use fully qualified syntax. Yeah, so Create animal and baby name string. Then struct dog, simple dog, and baby name string. String from bot. Let me quick. Then we can import animal for dog, and then string from puppy. Yeah, and then println baby dog is called a dog baby name. So this one is a bit more ambiguous. Not debug. Go away, please. Go away. Wanted run. Yep, so that one was... Yeah, that'll just call from there, so... Yep, this code is from Animal Shelter where it wants to name all of puppy's spot, which is impl and baby name AF. Find on dog. Yep. Also impls animal, which describes characteristics all animal have. Baby dogs are called puppies, and that's expressed with animal. Yep. Create on dog. Yep. And main we call dog baby name. That calls. Yep. But this output isn't what we wanted. I want to call baby name function part of animal. Yep. But this is not illegal. Or yeah, this is not legal. So we need something else. Yep, that is just an error, so what do we need? Yeah, so we do dog as animal. Okay. That makes sense, yeah. Yeah, that works. So yeah. That makes a lot of sense, just like basically, what you do in, like, Java or something is you'd wrap the cast in parentheses, but why not just use, like, the generic tags? Yeah. Makes sense. Yeah, we're providing Rust with the type annotation within the angle brackets, which indicates we want to call the baby name method from animal trait as impl on dog by saying we want to treat dog type as an animal. Yep. For AFs, there would not be a receiver yet. Yeah, fully qualified syntax is type is trait, function, receiver if method, next arg, yep. No receiver, so yeah. Alright. You use fully qualified syntax everywhere that you call functions and methods, but you're allowed to admit any part of it the rest can figure out from other info. You only need to use this more verbose syntax in cases where there are multiple impls that use the same name, and Rust needs help to identify which one you want to call. Okay. Super traits! Sometimes you might need one trait to use another trait's functionality. Woo! Alright. Yep. Need to run dependent also being impled. So yeah, super traits. Yep. Let's say we want to make outline print. That'll print vel framed in asterisks. Yep. That's given a point struct that implements display. Yep. It'll display something like this. Okay. In the implementation of outline print, we want to use the display traits functionality. Alright. Hooray! Hierarchy! Somewhat. Kind of. Right. Use standard format. Great. Outline print. Outline print. Format display. Then we can fun outline print and self. Let output equals self to string. Let len equals output.len. Println. Star.read len plus 4. Println. Star space dot repeat len len plus 2. Why's that grade? Very good. Okay, then println star space space star output, and basically copy these again. And oh, my nose is so clear right now. This is so fucking good. Ah, yeah. Yay, now we need to, yeah, so now if we have struct point x I32 y I32, then we can impl outline print point. But there's an issue here in that we still need to impl display. So then we can derive display. Boom. Oh no. Not find display in format. What? Oh right, no, because you can't. Can you not? Can't derive display. Yeah, thought so. Yeah, I'm thinking of different ones. So yeah, now I need to impl display for point. To what does this? No, format. That, save you. Now I can alt enter, impl missing members. Yep, there. Now I can, yeah. Return string format up, or no, then self to x, self to y. Good. Oh, format result. I'm doing something wrong here. Let me just look at the code. Yeah. Oh. That'll just automatically. All right. That'll just do it automatically. Okay. Already written for me. Placement for custom formatting where debugs just display content type. Yeah. All right. So. Right. All right. So I've got a macro for this. Right. Formatter. Yep. Then self x self y. Yay, okay. It's just got like a macro for it. Okay, neat. Alright. Woo! Now I can, and now I can let t equal point x 3 4 y 8 and semicolon p dot outline print save up and then run this. Yay, it works. Woohoo! All right, awesome. All right, now new type pattern to implement external traits on external types. Oh boy, that's all right. So time to do something that you're not supposed to normally. So we've got a pattern for it. Yep. Mentioned orphan rule. Yeah, basically it's time to bypass that. So possible to get around this using the new type pattern, which creates a new type in a tuple struct. Okay. Cover tuple structs and using tuple structs without name fields to create different types. Woo! Nikki, thank you very much for Redeem and give Lem a compliment. How do you manage to be an amazing programmer and also an amazing person? Thank you. Beep, 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 beep. Alright, Yep, orphan rule states allowed to implement a trait on a type as long as either trait or type are local to trait. Yep, so new type pattern. Tuple structure of one field and be a thin wrap around the type we want to implement trait for. Wrapper type is local to our trait, and we can implement the trait on the wrapper. New type is a term that originates from Haskell. No runtime performance penalty for using it, and the wrapper is elided at compile time. Yay! Hooray, elision. Yeah, use standard format, struct, wrapper, vex, string. Then you can impl format display for wrapper. Alright. And alright, see, now I can, yep. Right. F. Up. Self. O. Join. Comma. Space. Up. Yep. Now I can take this and let W wrapper. No. I type that W. Back. String from hello. String from world. Up. Then println W equals badum W. And boom. Yay! Awesome. Impl of display uses self to O to access inner vec T because wrapper is a tuple struct and vec T is at index O in the tuple. Yep. Then we can use functionality of display on wrapper. Downside is that wrapper is a new type, so it doesn't have the methods of the value it's holding. We would have to implement all the methods of vec T directly on wrapper such that the methods delegate to self O, which would allow us to treat wrapper exactly like a vec T. We wanted the new type to have every method in the that the inner type has. Implementing deref on the wrapper to return the inner type would be a solution. We don't want it to have all the methods in the inner type, for example, to restrict. We have to implement just the methods we do want manually. Now you know how the new type pattern is used in relation to traits. It's also a useful pattern even when traits are not involved. Let's switch folks and look at some advanced ways to interact with Rust's type system. Advanced types, yay! Yeah. I do have to say, I'm not entirely sure how I feel about, like, wrappers and such. They can just be a lot. Like, just, some of the code we've written is just, like, wrappers and wrappers and wrappers, which can be a bit annoying. Like, just, especially when we were, like, you doing, like, all the ref cell stuff and everything. Yeah. New types can get really annoying, yeah. I wish there was, like, a easier way to, yeah, Yeah, it feels like macros would be able to, like, help with a lot of that, but yeah. Wrappers are kind of just a fact of life for programming in general, yeah. But, like, I think just with, like, some of the stuff that Rust does, yeah. I mean, they're macros, so we'll look at those in a bit. So, new type for type safety and abstraction. New types useful tasks beyond those we've discussed so far, including statically enforcing values so never confused, and indicating units of value. Yep. Millimeters and meters are, yeah, structs wrapped U32s in a new type. Wrote a function with a parameter of type millimeters. We couldn't compile a program that accidentally tried to call a function with meters or plain U32. Yep. Alright. Abstracting away some impl details of a type. The new type can expose a public API that's different from the API of the private inner type if we use the new type directly to restrict the available functionality. They can also hide internal impl. For example, we could provide a people type to wrap a hash map I32 string that stores a person's ID associated with their name. Code using people would only be able, only interact with the public API, such as a method to add a name string to the people. That code wouldn't need to know that we assigned an I32 internal. Yep. Lightweight way to achieve encapsulation. Yep. Creating type synonyms with aliases. Okay, yeah, so just... Yep, just like... Yeah, so... Type... kilometers equals I32. Then... Let x I32 equal 5. Let y kilometers 5. Println x plus y equals sum x plus y. Yeah. This is legal because it's just a type alias. Yeah. It is not an entirely new type with tuple structs. It is just like type alias, okay. Yep, same type, we can add values and pass kilometers, values of functions that take I32. We don't get the type checking benefits from new type. Main use case for type synonyms is to reduce repetition. Yep, might have a lengthy type like this, box, in, fn, plus n, plus prime static, yep. Yeah. Yeah, that's just annoying to type, so you can alias it. Makes sense. Wish there was just an easier way to implement a new type that was entirely transparent, yeah. I could, like, maybe see something with macros, but, might be a bit tough. Yeah. Okay. Type alias makes this code more manageable by reducing the repetition, yep. Yeah, basically just like, you've got a long type signature, you can just alias it, yay! Much easier to read and write. Choosing meaningful name for type alias can communicate your intent, yep. Thunk is a word for code to be evaluated later, so it's an appropriate name for a closure that gets stored, okay. Also commonly used with result TE for reducing repetition, yep. Yep. IO ops often return a result, so that's IO error, yep. There's an IO error struct that represents all IO errors. Many will be returning result TE, where E is standard IO error, so yeah. Yeah, that's why there's like the, type, yep. So, that's why there's like this type. My parents were actually watching a movie I was interested in. Ooh, nice, nice. Yeah, because this declaration is in standard IO, we can use fully qualified alias. Yep, standard IO result. Yep, with E, standard IO error. Right trait function signatures end up looking like this. So yeah, like this. Yay! So it basically just a result like that. Nice. Type alias helps in two ways. Code makes code easier to write and gives us consistent interface. Yep. Because it's an alias, it's just another result to E, which means you can use any methods that work on result to E with it. Yep. All right. Rust has a special type named Bang. That's known in type theory lingo as the empty type with no values. We prefer to call it the never type because it stands in the place of the return type when a function will never return. Code is read as function bar returns never. Functions that return never are called diverging functions. Yeah, we can't create values of the type bang, so bar can never possibly return. But what is the type you can create never values for? Yep, so here. Yep, here, like, yep, so, like, we've got this, like, from listening to 5, we've got let guess u32 equals match guess trim parse, okay, num to num, or error, ignore to continue. At the time, we skipped over the details in this code. In Chapter 6, in the match control flow operator section, we discussed that match arms must all return the same type. So this doesn't work. Yep. Free Guy when Ryan Reynolds is an NPC in... Oh yeah, I've heard about Free Guy. There's like... A lot of what I've seen of Free Guy just feels like Disney flexing about how many IPs they've bought, but it does still look interesting. Might, like, give it a watch on my own time sometime. Yeah. Yep. Type of guest would have to be integer and string, but Rust requires guests have only one type, so what does continue return? What does continue return? Nothing! It returns never! Yep. Former with a value of U32, ladder with a bang. Bang can never have a value, so it just knows that it's U32, yep. Formal way of describing this behavior is that expressions of type bang can be coerced into any other type. Yep. We're allowed to end this match arm with continue because continue doesn't return a value, and it's a control flow keyword. So yeah, it's kind of null-ish, but not quite. But yeah, never type's useful with panic as well. Remember, unwrap function, we call option T values to produce a value or panic, yep. Yeah, that returns bang. Yep, same thing happens in match and listing 926. Rust sees that values type T and panic has type bang, so result of overall match is T. Panic doesn't produce a value, it ends the program. In none case, we won't be returning a value from unwrap, so yeah. Then type bang is also for loop, because that's just an infinite loop. This wouldn't be true if we included a break, because loop would terminate when it got to the break. Right, and then dynamically sized types and the sized trait. Yep. Alright, so due to Rust need to know certain details as how much space to allocate, corner in its type system that can be confusing. Dynamically sized types, or DSTs, or unsized types. Yep, values whose size we can only know at runtime. So yeah, stir is an unsized type. Yep, and we just borrow it as and stir. So yeah, can't know how long the string is till runtime, meaning can't create a variable of type stir, nor can we take an argument of it. Yep. Rust needs to know how much memory to allocate for any value of a particular type. And all values of a type must use the same amount of memory. If Rust allowed us to write this code, these two stir values would need to take up the same amount of space, but they can't. Friend made his own unsized type once. The code is incredibly cursed. Oh no. Oh boy. Yeah. They have different lengths. S1 needs 12 bytes, and S2 needs 15. Yep. That's why it's not possible to create a variable holding a dynamically sized type. You need a pointer to it. So that's like slices, or, yeah, bars or such, yeah. Though an t's single value stores memory address of where the t is located, and and stir is 2. Address of the stir and its length. We know the size of an and stir at compile time, but not a plain stir. That's unsized. Yep. In general, this is the way which dynamically sized types are used in Rust. They have an extra bit of metadata that stores the size. Yep. Golden rule of Yep, golden rule of dynamically sized types. Why am I like screen for everything? Yep. Okay. Must always put values of dynamically sized types behind a pointer. Okay. You can combine stir with all kinds of pointers. For example, box stir or RC stir. Yeah. You've seen this before with different dynamically sized type traits. Traits are dynamically sized. Okay. Yep. Using trait objects to allow for values of different types. We mentioned that to use traits as trait objects, we must put them behind a pointer, such as end in trait or boxed in trait. Yep. To work with DSTs, Rust has a particular trait called sized. Okay. To determine whether or not type size is known at compile time. It's automatically implemented for everything whose size is known at compile time. Rust implicitly adds a bound on size to every generic function. Alright, so chaos zone is ungeneric, the unsized, T and T, and snip. Yep. trait bound on question mark size means T may or may not be sized. Overrides the default that generic types must have a known size at compile time. This is chaos! Right, switch type of T from T to anti, because type might not be sized when you need to use it behind some kind of pointer. We've just chosen a reference. Okay, well, let's talk about functions and closures. Okay. 10:38, yeah. I should have plenty of time. I can, go over, but yeah. We'll explore some advanced features related to functions and closures, which include function pointers and returning closures. Talked about how to pass closures to functions. You can also pass regular functions to functions. Technique is useful when you want to pass a function you've already defined rather than defining a new closure. Doing this with function pointers will allow you to use functions as arguments to other functions. They coerce to the type fn with a lowercase f, not to be confused with the fn capital F closure trait. Fn type is called a function pointer. Syntax for specifying the parameters of function pointer similar to that closures. Okay. Yeah, basically, so fun add 1 x I32 to I32 x plus 1 and fun do twice fn I32 to I32 arg I32 to I32 f arg plus f arg. Yep. And in main we can just up here let answer equal to twice add 1 5 println the answer is but answer that should be 12. Alright, yep, 12, yay, okay. Yep, specify param f and do twice the fun that takes one parameter, type I32, returns an I32. Yep, call f in here, yay. In main, we can pass the function name add1 as the first argument to do twice. Unlike closures, fun is a type rather than a trait, so we specify fun as the parameter type directly, rather than declaring a generic type parameter with one of the fun traits as a trait bound. Okay. Function pointers implement all three of the closure traits, fun, fun mute, and fun once, so you can always pass a function pointer as an argument for a function that expects a closure. Best write your functions using a generic type and one of the closure traits so your functions can accept either functions or closures. Okay. Example where you would want to only accept fun and not closures when interfacing with external code that doesn't have closures. C functions can accept functions as arguments, but C does not have closures. Example of where you could use user closure defined inline or a named function. Let's look at map. Use map to turn vector numbers into a vector of strings. We could use a closure, so let me type that out. Let list of numbers vec 1, 2, 3. Let list of string equals list of numbers iter dot map bar I to string dot collect. There. And or instead we could name the function as the argument to map instead of the closure, so instead we could do to string. Yep. Like that, yay. Must use fully qualified syntax we talked about earlier in the advanced traits section because there are multiple functions available named to string. Yep. Here we're using toString function defined in toString trait, which standard libraries import for any type that implements display. We have another useful pattern that exploits an impl detail of tuple structs and tuple struct enum variants. Oh boy! These types use unit as initializer syntax, which looks like a function call, or parens, yep, looks like a function call. The initializers are actually implemented as functions, returning an instance that's constructed from their arguments. Holy shit. Oh boy. Alright, so let's up in status value U32 stop. Let list of statuses spec status equals OU32 ... map status value select. Oh my god, that's great. That is supremely silly and cool. Semicolon, yeah. Alright, yeah, anywhere you see that, it is just like, yeah, you can just pointer that. Alright. Yep. Some people prefer this style, some prefer to use closures. They compile to the same code, so it's just readability. Hooray, CCA! Alright. Closures are represented by traits, which means you can't return closures directly. In most cases where you might want to return a trait, you can instead use the concrete type that imports the trait as the return value of the function. But you can't do that with closures because they don't have a concrete type that's returnable. You're not allowed to use the function pointer fun as a return type, for example. Right. Yeah. This won't compile. Yep. Yep. It's because sizing. Yep, doesn't have size known at compile time because it's in, so you've got to box it. Yeah, that'll just be unreturn closure to box in fun I32 to I32 box new bar x plus 1. There, like that. There. Yay! This will compile just fine because it's in a box. I did not want. Yay! Cool things. Alright, yep. So, there's more about that, for trade objects and such, but guess what, y'all? It's time for true chaos. Let's look at macros. Use macros like println throughout the book, but we haven't fully explored what a macro is and how it works. Macro refers to a family of features in, Rust, declarative macros with macro rules, and 3 kinds of procedural macros. Custom derived macros that specify code added with the derive attribute, attribute-like macros that define custom attributes usable on any item, and function-like macros that look like function calls but operate on the token specified as their argument. Okay. We'll talk about each of these in turn, but first, let's look at why we even need macros when we already have functions. Macros are for metaprogramming. They're done at compile time and not runtime. Yep, derive will generate impls. Yep, also use println and vec. All these macros expand to produce more code than the code you've written manually. Metaprogramming is useful for reducing the amount of code you have to write and maintain, which is also one of the roles of functions, but they have additional powers. A function signature must declare the number and type of parameters the function has, but macros can take a variable number of parameters. You can call println with 1 argument or println with 2. Also, macros are expanded before the compiler interprets the meaning, so a macro can implement a trait on a given type. A function can't because it gets called at runtime. A trait needs to be implemented at compile time. Downside to implementing a macro is that macro defs are more complex because you're writing Rust code that writes Rust code. Due to this indirection, macro definitions are generally more difficult to read, understand, and maintain. Another important difference between macros and functions is that you must define macros or bring them into scope before you call them in a file, as opposed to functions you can define anywhere and call everywhere. Right? Alright, macro rules. declarative macros. Okay, yeah, these are referred to as macros by example. Macros are just plain macros. Declarative macros allow you to write something similar to a Rust match expression. Yep. They're control structures that take an expression, compare the resulting value of the expression to patterns, and then return the code associated with the matching pattern. The macros also compare value to patterns that are associated with particular code. In this situation, the value is the literal Rust source code passed to the macro as tokens. Patterns are compared within the structure of that source code, and the code associated with each pattern when matched replaces the code passed to the macro. All this happens during compilation. Okay. So, to define a macro, you must use the macro rules construct. Let's explore how to use macro rules by looking at how vec is defined. Chapter 8 covered how we can use vec to create a new vector with particular values. Yep, so got like let v vec new 32 equals vec 1, 2, 3 like that. But what if we wanted to do that ourselves? Alright. We could also use vec macro to make a vector of 2 integers or a vector of 5 string slices. Yep. We wouldn't be able to use a function to do the same because we wouldn't know the number of type of values up front. So this is basically just a simpler version of it, but yeah, hash macro export macro rules vec. Then this will be bang paren bang x spur close paren comma star space. Yep. Oh, this is a fun one. Alright then, boom. Let mute temp vec vec new bang, yeah, bang ren temp vec push bang x, not bang, yeah, dollar sign, yep, then start temp vec. Okay, this is a simpler version. Okay, oh, I forgot. The actual definition of vec uses code to pre-allocate the correct amount of memory up front. That code's an optimization we don't need to include here because we don't really care. Yep, macro export indicates the macro should be made available whenever the crate in which the macro is defined is brought into scope. Without this, the macro just can't be brought in. Yep, you start def with macro rules and the name of the macro without the exclamation point. Yep, vec followed by curly brackets denoting the body of the macro def. Structure in the vec body similar to the structure of a match expression. You have one arm with the pattern paren $x colon xper close paren star close paren. Yep, followed by error block of code. If the pattern matches, the associated block of code will be emitted. Given that this is the only pattern in the macro, there's only one valid way to match. Any other pattern will result in an error. More complex macros will have more than one arm. Yep. Valid pattern syntax in macro defs is different from the pattern syntax because macro patterns are matched against Rust code structure rather than values. Let's walk through what the pattern pieces in 1928 means. For full syntax, there's just like macros by example here. Alright. So yeah. First set of parens encompasses the whole pattern here. A $sign is next followed by a set of parens that capture values that match the pattern within the paren. Yeah, this, alright, so this means capture this within is bang x expression, which is basically saying an expression will bind to x. Yep. Matches any Rust expression, gives the expression the name bang $x. Yep, comma following $paren indicates a literal comma separator character should optionally appear. Yep. Here, yeah, after the code that matches in $. Yep. Then the star specifies the pattern matches 0 or more of whatever precedes the star. Alright, so yeah, that's just basically that. Yeah. Well, we call this macro with vec bracket 1, 2, 3. The $X pattern matches 3 times with the expressions 1, 2, and 3. Now let's look at the pattern in the body of the code associated with this arm. Temp vec.push. Then $paren stars is generated for each part that matches $paren in the pattern 0 more times, depending on how many times the pattern matches. $X is replaced with the expression matched. Yep. When we call this macro with vec bracket 1, 2, 3, code generated that places this macro will be the following. Okay, yep. Yeah, that'll be like, that is basically what this will compare to. Neat. Okay. Alright. We've defined a macro that can take any number of args of any type and can generate code to create a vector containing the specified elements. There's some strange edge cases. In the future, Rust will have a second kind of declarative macro that'll work in a similar fashion but fix some edge cases. Alright? After that, macro rules will be effectively deprecated. With this in mind, as well as the fact that most Rust programmers will use rather than write macros, we won't discuss macros any further. Yep, so there's the little book of Rust macros, which I might look at some point. Might be cool, but yeah. Yep. Okay. Procedural macros for generating code from attributes. So these are procedural macros, which act more like functions and are a type of procedure. Procedural macros accept some code as an input, operate on that code, and produce some code as an output rather than matching against patterns and replacing with other code as declarative macros do. Yeah, declarative macros are basically like regex. Yeah. Alright, 3 kinds of procedural macros: custom, derive, attribute-like, and function-like all work similarly. So, when creating proc macros, definitions must reside in their own crate with a special crate type. This is for complex technical reasons that we hope to eliminate in the future, alright? Using proc macros looks like the code in listing 1929, where some attributes placeholder for using specific macro, yep. So, where'd that go? Here, yeah. So, yeah. Function that defines a procedural macro takes a token stream, so yeah, who's proc macro. Yep. Hash some attribute hub and some name input token stream. I know this isn't like actual thing, but yeah, to token stream. You have to use a crate type to be able to use proc macro, yeah. It'll talk about that a bit, but yeah. Function that defines a procedural macro takes a token stream as an input and produces a token stream as an output. Token stream type is defined by the proc macro crate included with Rust and represents a sequence of tokens. This is the core of the macro. Yeah, the source code that the macro is operating on makes up the input token stream, and the code the macro produces is the output. The function also has an attribute attached to it that specifies which kind of procedural macro we're creating. I have multiple kinds of procedural macros in the same crate. Let's look at the different kinds, okay. Start with custom derive and then explain small dissimilarities that make other forms different, okay. Let's create a crate named hello macro that finds a trait named hello macro, okay. Alright, so, yeah. Alright, so, in source main rs, yeah. Alright, yeah, so we'll have like the used hello macro, and everything, yep. Alright, so. Alright, do I do that like in here or? Yeah. cargo new hello macro lib. Right. Oh, in your cargo table, yeah. Have to change your crate type to be able to use proc macro, yeah, in cargo table, yeah. Well, luckily, we've got that there. I don't know if I made this in the right place, but oh well. Yeah, so oh well. We're gonna pub trait hello macro on hello macro. I'm gonna say use hello macro hello macro hello macro derive hello macro. Yeah, I'm absolutely not doing this in the right place, F. I'm gonna delete. Yeah, we'll find this out in a bit, but yeah, project structure, yeah, you did. Oh, I did, yeah, I'm just gonna, like, I'll use, I'll just make these rust hello, and, pub trait hello macro, and hello macro. Right, then this had a drive hello macro struct pancakes. Alright, then pancakes hello macro. Boom. Alright. Yeah, the drive doesn't exist yet. Okay, yeah. Alright, so yep. So now, got this, yep. We have a trait as function. Our crate user could implement the trait to achieve the desired functionality, like so. But we want to make it easier, yep. They'd need to write the input block for each type they wanted to use with hello macro. We want to spare them from having to do this work. Additionally, we can't yet provide the hello macro function with default input that'll print the name of the type the trait is implemented on. Rust doesn't have reflection capabilities because it's not real. Nothing's real, so it can't look up the type's name at runtime. We need a macro to generate code at compile time. Alright, so now, there, yeah. Let me go to this. Alright, so alright, so terminal. Alright, so now we're gonna cargo new. Oh, I'm gonna just snooze this ad for a bit, but yeah. Alright, hello macro. Yeah, I'll say rust hello derive. Rust hello derive dash lib. Right, then now I've got rust hello derive, okay. Two crates are tightly related, so create the procedural macro crate within the directory of our hello macro crate, yep. Change the trait def, yep. We'll have to change the impl of the procedural macro and hello macro derive. Two crates will need to be published separately, and programmers using these crates will need to thank you for the hydrate, non! And posture check and everything. I have to change the impl of the procedural macro and hello macro derive, yep. Stretch and some whops. Yeah. Alright. Yep, I have to change the impl in the procedural macro, hello macro derive, yep. Two crates will need to be published separately, and programmers using these will need to add both depths and bring them both into scope. Instead of hello macro crate use hello macro derive and re-export. However, the way we've structured the project makes it impossible for programmers to use hello macro even if they don't want derive. Okay, so need to declare hello macro derive as procedural macro crate. Also need functionality from sin and quote. So, alright, so it's gonna be lib proc. Why is my proc macro equals true? Then we'll need sin equals 1.0 and quote equals 1.0. Okay. Alright, good. And pro macro 2 sin and quote my save. Alright. So now in this librs, yep, so we're gonna extern create proc macro, use proc macro token stream, use quote, use sin. Alright. Hash proc macro drive hello macro hub fun Rust hello derive, yeah. Rust hello derive, but token stream to token stream. Alright, so Alright, so this is construct a representation of Rust code, a syntax tree that we can manipulate. Let ask equals sin parse input unwrap and build the crate implementation impl hello macro and asked. Alright, so now we've got to write the code for that. Yep, split the code into hello macro derive function, which is responsible for parsing, and the impl, which is responsible for transforming the syntax tree. This makes writing a proc macro more convenient. Code and outer function will be the same for almost every proc macro crate you see or create. Code you specify in the body of the inner function will be different depending on the purpose. Okay. Yep. So proc macro, sin and quote. Proc macro comes with Rust. Didn't need to add that to cargo toml. It's the compiler's API that allows us to read and manipulate Rust from our code. Sin parse Rust code from a string into a data structure that we can perform ops on. Yep. Quote turns sin data structures back into Rust code. Crate makes it much simpler to parse any sort of Rust we might want to handle. Write a full parser is no simple task. Okay. Yep. Alright. Called when a user of a library specifies derive hello macro. Yep. Possible because we've annotated hello macro derive with proc macro derive in specified name hello macro. Yep. Yeah. Yep. Parse instant takes a token stream and returns a derive input struct representing parsed Rust code. Yep. Alright. Shows relevant parts of the derive input we get from passing struct pancakes. Yep. Whee! Tasty. Okay. Fields show Rust code of parts of the unit struct with the ident of pancakes. Yep. More fields on the struct for describing all sorts of Rust code. Checks in for more info. Okay, yeah. Soon we'll define impl hello macro, which is where we'll build the new Rust code we want to include. Note that the token for our output is also a token stream. Added to the code our crate users write, so when they compile the crate, they'll get extra functionality that we provide. Yep. Might have noticed we're calling unwrap because the hello macro derive to cause if some parse fails. Basically because that means there's a bad syntax on their side. Okay, yeah. Necessary to panic on errors because they return token stream rather than result. Yep. Simplified by using unwrap. You should provide more specific error messages otherwise, but yeah. Expect or panic, yeah. Now that we have code to return the annotated Rust code from a token stream into a derive input. Okay, yep. I don't, yeah, often will hello macro ask instant drive input to token stream let name equals and ask ident let gen equals quote simple hello macro or name and hello macro println hello macro my name is string by hash name then semicolon gen and dot into there. Yeah, no, this goes that goes there, then gen into there. Alright. Be right back, y'all. I'm back again. Yeah, I've been experimenting with, like, the new, like, automatic ad running system in, yeah, on Twitch, and it is helping, like, me take better care of myself while streaming, because, like, I don't want to stream while ads running. That'd be, like, cutting stuff out for folks who are not subscribed, so I'm just letting myself go on break, like, refill my water, get something to drink, like, walk around a bit and stretch, and it's really helpful, so yeah. I, like, hopefully I'll get a, yeah, hopefully, like, it's just gonna help me take better care of myself, and hopefully I'll get a bit more money with it, because, oh boy, financials are not great right now. Yeah, back to this, so yeah, we just did, like, the Impel Hello macro with all this, okay? Yeah, it is very neat to, like, be messing around with token streams and asks and such, it's fun. Alright, but yeah. So we've got that. Ends with Gen into. Alright. Get an ident struct instance containing the name identifier of annotated type using asked ident. Yep. Shows that when run impl hello macro function on the code in listing 1930, ident will have the ident field with the value of pancakes. Thus, name will contain an ident struct instance that, when printed, will be the string pancakes, the name of the struct in 1930. Okay, yeah. Quote lets us define the rest code we want to return. Compiler expects something different to the direct result of the quote macro's execution, so we need to convert it into a token stream. We do this by calling into, which consumes the intermediate representation and returns the value of the required token stream type. Yay. We'll also provide some very cool templating. You can enter a hash name and quote will replace it with the value in the variable name. Yay. You can even do some repetition similar to the way regular macros work. Check out quote traits docs for a thorough introduction. Okay. We want our procedural macro to generate an impl of our hello macro trait for type the user annotated, which we can get by using hash name. Yep. Trait impl is one function, hello macro, whose body contains the functionality we want to provide. Printing hello macro, my name is, and the annotated type. Yay. Stringify it macro here is built into Rust. Takes a Rust expression such as 1 + 2, and at compile time, turns the expression into a string literal, such as 1 + 2. Yep. This is different from format or println macros, which will evaluate the expression and then turn the result into a string. There's a possibility that the hash name input might be an expression to print literally, so we use stringify. Using stringify also saves an allocation by converting hash name into a string literal at compile time. Right. At this point, cargo build should complete successfully in both hello macro and hello macro derive. Alright. Yep. Let's hook up these crates to the code in listing 1930. Yep. So, here's what... Alright, so we've got to pull out this cargo toml. Okay. Alright, so... Yep. Yep. Okay, so... Create a new binary project, new projects directory. We've already got that. Okay, yeah. Yep, so... Rust hello derive equals derive half equals // or I don't know, Rust hello derive. Okay, yeah. Good. Why? This is apparently an issue. Oh wait, no. That's alright. Yeah. Then it's Rust hello You're good. Please. Oh boy. Oh boy, yeah, I should really just, like, follow, like, what it's telling me to do, but yeah, this is probably not gonna work, huh? Yeah, can't run this, can I? Can I? I'm gonna close. Alright, hopefully this will reboot, Rust Analyzer. Right, let me just make a new terminal then, cargo run. Oh boy. No, yep. I know it yeah, like, save that? Are you good? It's still frozen waiting for cargo metadata or cargo check, yeah. It would // yeah. Yeah, hopefully it'll, yeah, like, can I get it to, like, oh boy, how do I get it to, like, stop? Because I want it to, like, it's still doing a cargo check and I want it to not, like, if it's, like, running a background task, then, there's a big problem here. Yeah, I don't know what to do, because I think, I don't know if I can force Rust Analyzer to, like, actually, I can task manager, if it is a separate task, okay, it's finally done, okay, so, now if I run main RS, yay, now it finally works, woo, okay, yeah, I just messed up there a bit, okay, yay, all good, woo, alright, yep, impl of hello macro was included without pancakes, branding impl, yep, so, attribute like macros, okay, so, yep, similar to custom drives, instead of generating code for drive, they allow you to create new attributes. Drive only works for structs and enums. Attributes can be applied to other items, such as functions. Here's an example of using an attribute like, say you have an attribute named root that annotates functions when using a web app framework. Okay, yep. This root attribute would be defined by the framework as a proc macro. Alright, so that would be like in here, that'd be like, hash proc macro attribute hub fun route adder token stream item token stream to token stream, something like that. Okay, yep, first is contents of attribute the get comma slash, yep. Second is the body the item attribute is attached to encase the fun index and rest function's body. Okay. Other than that, attribute like macros work the same way as custom derive. You create a crate with proc macro crate type and implement a function that generates the code you want. Alright. Lastly, function-like macros define macros that look like function calls. Similar to macro rules, they're more flexible than functions. For example, they can... Oh!
Whoa, shocked face.
Yeah. Yo! Artemis, thank you very much for subscribing at Tier 1 for 16 months on a 16-month streak. Wow! Thank you so much for hanging around. You are incredibly just sweet and wonderful and good, and I'm really happy I know you. Yeah, Alright. Yep, so function-like macros take a token stream, and definition manipulates that token stream using Rust code as the other two types of proc macros do. Yep. So SQL macro here, like select star from post where ID equals 1, yeah, that basically just, yeah. Parse the SQL statement inside and check that it's syntactically correct, which is much more complex processing than a macro rules can do, yep. So you'd do something like that. There is some curse stuff you can do with that, like, oh my god, you can do some curse stuff with that. Who wants to see hell? Who wants to see hell? Embed C is a crate that allows you to embed C code inside Rust code files. C code is translated into Rust code at compile time using C to Rust, which means it is fully interoperable with Rust. C code can call Rust code and vice versa. Ha 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 ha, boy. It's not yet on Crates.io, but oh boy. Wait, embeds, yeah. It embeds, like, C code. Like, C code. Yeah. Yep. Like, that is, like, C code right there as, yeah. I thought I'd seen curse stuff, yeah. This is, it's delicious. Yeah. Yeah. Example at the top is translated to basically just, like, yeah, it just turns into like an external C function, which means you gotta call it with unsafe. Yeah. It's great. Yep. Yeah, here's another of their examples. Yeah. Fun stuff. Turning a C switch case into like pattern matching. Yeah. Fun things, huh? Yeah. As you can see, the inner leaf switch do construct is transpiled into a very enigmatic Rust function through the use of pattern matching. You may not like it, but this is what peak functional programming looks like. Limitations, many. Motivation, not applicable. I love curse shit. It's great. Yeah, whew. Now you have some Rust features in your toolbox that you won't use often, but you'll know they're available in very particular circumstances. We've introduced several complex topics so that when you encounter them in error message suggestions or in other people's code, you'll be able to recognize these concepts and syntax. Use this chapter as a reference to guide you to solutions. Next, we'll put everything we've discussed throughout the book into practice and do one more project. Final project. Building a multi-threaded web server in Rust. I'm so excited for this. This is gonna be cool. This'll take way more than half an hour, but I'm gonna go until it's done. Ooh boy, it's one of my favorite curse macros. Ooh boy. Ooh, ooh. Ooh. Let's take a look at this. Do not use, do not use, do not use! Oh, oh boy. Oh no. Oh no. Oh no. This is... Oh no. Works, but at what cost? Oh no. This. Oh no. Oh my god, it's just a macro rules, holy shit. Parse the function name either string literal or an ident for an int-stir variable in the args in the function call syntax. And it takes the function name and passes it to get sim, which is just a function for reading the executable from the first arg passed and getting a pointer to a dim sim by name that transmits to function pointers so we can call it. YouTube doesn't have to pass which types they're calling the function with, we need to have them inferred. All this does is consume whatever we pass and outputs a blank. Those are unfamiliar. Yep, infer, yeah. We can pass each of the arguments into the macro. Oh no. Oh. Function pointer with different type and two arguments whose type should be in. Oh no! Why do we need the macro? Which is a good question. Reason is since we need the amount of underscores to match the number of args, we need to sum up past each argument as its type. Can't have types be the args themselves, we need a macro to convert these tokens to a valid type. Why? This is horrible! Oh my god, Maddie! Oh my god. Oh, I hate this. Oh, that's awful. I love it. Oh, that's beautiful. One of my favorites for a reason, yeah. Alright. Here's the plan to build the web server. Learn a bit about TCP and HTTP, listen for TCP connections on a socket, parse a small number of HTTP requests, create a proper HTTP response, and improve the throughput of our server with a thread pool. Woo! We should mention one detail. The method we will use won't be the best way to build a web server with Rust. A number of production-ready crates are available that provide more complete web server and thread pool impulse than we'll build. However, our intention is to help you learn, not take the easy route. Because Rust is a systems language, we can choose the level of abstraction we want to work with, and can go to a lower level than is possible or practical in other languages. We'll write the basic HTTP server and thread pool manually so you can learn the general ideas and techniques behind the crates you might use in the future. Both disgusting and useless, yeah. Okay, so. Alright. Let's get terminal up. Cargo, new. Lemonette. Alright. Now I'm going to file, open folder. We're gonna open Lemonette. Let's go. Yes, I trust the authors. Trust the author. Yep, all files. I am the author of anything in Rust. Yeah. So, we'll start by getting a single-threaded web server working. Before we begin, let's look at a quick overview of the protocols involved in building web servers. Details are beyond the scope of this book, but a brief overview will give you the information you need. The main protocols are HTTP and TCP. Both protocols are request-response, meaning a client initiates requests and a server listens and provides responses. Contents and responses are defined by the protocols. TCP is a lower level protocol that describes the details of how information gets from one server to another, but doesn't specify what that information is. HTTP builds on top of TCP by defining the contents of the requests and responses. It's technically possible to use HTTP with other protocols, but in the vast majority of cases, HTTP sends its data over TCP. We'll work with the raw bytes of TCP and HTTP requests and responses. A web server needs to listen to a TCP connection, so that's the first part we'll work on. Standard Library offers a standard net module that lets us do this. Let's make our new project. Alright, we've got Lemonette. Alright, so we're gonna start out with main RS, which has our nice little hello world here. Right, so we're gonna first off use standard net TCP listener. Alright, then we've got a listener equals TCP listener find 127.0.0.1.7878. And we're gonna unwrap that. Okay, so we're gonna be binding to address 127.0.1.7878, okay? Or stream in listener incoming. Let stream equals stream unwrap. And we're gonna println connection established. Okay. Yep. So we can listen for TCP connections at the address 127.0.1.7878. In the address, the section before the colon is an IP address representing your computer. Same on every computer and doesn't represent the author's computer specifically. That's just always 127.0.1. Yeah, And 7878 is the port. We've chosen this port for two reasons. HTTP isn't normally accepted on this port, and 7878 is Rust typed on a telephone. Oh my god. Yeah. Bind in this scenario works like the new function in that it will return a new TCP listener instance. Called bind is then networking connecting to a port the listener is known as binding to it. Okay. That returns a result TE, which indicates that binding might fail. Connecting to port 80 requires the admin privs. Non-admins can listen only on ports higher than 1023. So if we tried port 80 without being an admin, binding just wouldn't work. Binding won't work if we ran two instances of our program and so had two programs listening to the same port. Because we're writing a basic server just for learning, we won't worry about handling these kinds of errors. We'll just unwrap it and it'll stop if it errors because we don't really care. This is dev time. If we wanted to make it fancier, we would. But yeah. Incoming returns an iterator that gives us a sequence of streams. More frequently, streams a type TCP stream. Yep. Alright, so... Yep. Incoming, yep. Single stream represents an open connection between client and server. Connection is named for full request and response process, which client connects to the server. Server generates a response, and then the server closes the connection. As such, TCP stream will read from itself to see what the client sent, and then allow us to write our response to the stream. Overall, this for loop will process each connection in turn and produce a series of streams for us to handle. Okay. For now, our handling of the stream consists of calling unwrap to terminate our program if the stream has any errors, but if there aren't any errors, the program prints a message. Connection established. Yay. We'll have more functionality for the success case in the next listing. The reason we might receive errors from the incoming method when a client connects is that we're not actually iterating over connections. Instead, we're iterating over attempts. This connection might not be successful for a number of reasons, many of them operating system specific. For example, many OSs have a limit to the number of simultaneous open connections. New connection attempts will produce an error until some of the open connections are closed. Okay, let's try running. Cargo run. Alright, we are live then. 127.0.0.1.7878. Connection established. Woo! Yay, it works. I can, stop it. Yay. Sometimes you'll see multiple messages printed for one request. Browser is making a request for the page as well as a request for other resources like favcon yet. It'll also be the browser trying to connect to the server multiple times because the server isn't responding with any data. When stream goes out of scope and is dropped at the end of a loop, connection is closed as part of the drop impl. Browsers sometimes deal with closed connections by retrying because the problem might be temporary. The important factor is that we've successfully gotten a handle to a TCP connection. Remember to stop by hitting Control-C, yep. Then restart Cargo Run after you've made a set of code changes to make sure you're running the newest code. Okay. Okay. Let's implement functionality to read requests from browser. To separate the concerns of first getting a connection and then take some action, we'll start a new function for processing connections. Alright, in handle connection, read data from TCP and print it so we can see the data being sent from the browser. Okay, so that means lots of stuff. Use standard IO prelude all. Okay, then use standard net TCP stream. Okay, got it. Alright, so now we can do other things. So we'll just make a fun handle connection mute TCP stream. Weird that we're putting mute here and like not borrowing it, but yeah. I guess, yeah. I mean, it makes sense, but yeah. Alright, so then we can handle connection stream. Alright, this. Move stream into here. Gotta make sure it's mutable. So yeah. Then let mute buffer equals 1024. We're gonna have a 1024 like size buffer. We're just initializing it all with zeros. Right now it's I32. We might want to like that with. I'm guessing this is gonna infer to bytes once we do stream read and mute buffer unwrap. Yep, now that's bytes, so that's 1024 bytes in our buffer. And println request some string from UTF-8 lossy and buffer run 7001 7978. Alright. So now we've got some stuff, okay. Oh, a lot of stuff. Okay, so got a request. Get /HTTP 1.1. Right, host 127.01.7878. Connection keep alive. Cache control MXHO. Yep. Yep, not a brand. V98. Yep. Or yep. Chromium. Yep. Microsoft Edge V98. Yep. XCHUA mobile. Question note. Platform Windows. Upgrade and secure request is 1 because we're not doing secure. Yep. User agents. Okay, yep. Lots of user agents. Yep. Text HTML application XHTML plus XML. Application XML. Yep. Q is 0.9. Image WebP. Image APNG. Star. Yeah, Q is 0.8. Application signed exchange. V equals V3. Q 0.9. Tech fetch site none. Mode. Navigate. User question 1. Desk document. Accept encoding gzip, deflate, or BR, and language EN, US, EN, and Q equals 0.9. Okay. That's a lot of info. Bring standard IO prelude into scope to get access to certain traits that let us read from and write to the stream. The for loop in main function, instead of printing a message that we've made a connection, will now call handle and pass stream to it. Okay. In handle connection, we've made the stream parameter mutable. Reason is that TCP stream instance keeps track of what data it returns to us internally. Might read more data than we asked for and save the data for the next time we ask for data. Therefore needs to be mute because its internal state might change. Usually we think reading is not needing mutation, but in this case we need the mute keyword just because like how that works. Alright. Next, we need to actually read from the stream. We do this in 2 steps. First, we declare buffer on the stack to hold the data that's read in. 124 bytes in size, big enough to hold the data for basic requests and sufficient for our purposes. Wanted to handle requests of an arbitrary size, buffer management would need to be more complicated. We'll just keep it simple for now. Pass the buffer to stream read, which will read bytes from the TCP stream and put them in the buffer. Yep. Then we convert the bytes in the buffer to a string and print that string. Alright, from UTF-8, lossy takes an AND-U8, produces a string. Lossy indicates behavior of this function when it sees an invalid UTF-8 sequence. I'll replace it with question mark. Yep, U plus FFD replacement character. Might see replacement characters for characters in buffer that aren't filled by request data. Let's try this code. Yep. Start the program, make a request. Note that we'll still get an error page, but our program's output will now look similar to this. So yeah, we've got a lot of stuff here. Yep, got things like that. So yeah, might get slightly different output. Yep. You can see why we get multiple connections from one browser request by looking at path after request get. Repeated connections are all requesting slash with no browsers trying to fetch slash repeatedly because it's not getting a response from our program. Yep. Let's break down this request data to understand what the browser's asking. So yeah. Yep, so now we've got, so text-based protocol, so yeah, that's method, request URI, HTTP version, CRLF, headers CRLF, and then message body. Yeah, message body will be a bunch of stuff, yeah. Oh yeah, so headers, and then yeah. Request line holds information about what the client's requesting. First part of the request line indicates method being used, such as get or post, which describes how the client's making its request. Our client used get. Next part is slash, which is the URI. Yep. URI is almost not quite the same as URL. Difference between URI and URL isn't important, but it uses URI, so we'll just use that, yeah. Then last is HTTP version, and the request line ends in CRLF. Yep, character return line feed. Terms from typewriter days, we can also be written as backr backn, where backr is character return and backn's line feed. Yep. Yep. CRLF separates request line from the rest of the request data. Note, when CRLF is printed, we see new line start rather than backr backn. Yep. Looking at your request line data we received from running a program so far, to get method slash request URL and HTTP 1.1's version. Yep. Remaining lines, yep. Onward are headers because get has no body. Okay. We're making requests to a different browser asking for a different address. Yep. Yeah, that changes. Yeah. Yeah. Right. 846. Yeah, I'll just go over. So yeah. Yep, implementing sending data and response. Yep, response to format. Yep, version, status code, recent phrase, CRLF, header, CRLF, message body. Okay, first line is a status line, contains HTTP version used, numeric status code summarizes the result of the request, and a recent phrase provides the text desk of the status code. After CRLF are any headers, another CRLF, and the body of the response. Okay, so, yep, so here's like a standard OK, which is HTTP 1.1, 200 OK, backr backn, backr backn. Right. 200 is standard success. Text tiny successful HTTP response. Let's write this to the stream as a response to a successful request. Okay. Alright, so remove the println and replace it with code and listing 23. So stream right. Oh yeah, or gonna let response HTTP /11 200 OK backr backn backr backn stream write response as bytes unwrap stream flush unwrap. Alright. Alright, so now, if I run this, and alright, blank page, yay! Control C. Alright, yay! Alright, so that means we've got a blank page. That's good. Yep, new line defines response variable, holds success messages data. Well, adds bytes on a response to convert string data to bytes. Write takes an AND-U8 and sends those bytes directly down connection. Write operation could fail. We use unwrap on any error result as before. Real app would add error handling, finally flush will wait and prevent program from continuing till all bytes are written to the connection. TCP stream contains an internal buffer to minimize calls to the underlying OS. Alright, so let's run our code and make a request. No longer printing any data, so we won't see any output, but we'll just get a blank page. Yay! Now let's return some real HTML. Alright, we're just gonna, we're gonna just like make hello HTML and doc type HTML lang n head meta parset equals UTF-8 title hello whop and head then body one whop and just paragraph hi from Rust. Alright, yay! Got an HTML file now. Assuming that get this done, yeah. So in this, we're gonna read it every time we call. Okay, yeah, sure. Alright, so now we're gonna let contents equals file system read to string hello HTML unwrap. Right then. Alright, now we've got to change this up. So format HTTP/11 OK back n content length r back n but comma content len contents but oh yeah, use standard fs, yeah, use standard fs. All good? All good. Run! I left an extra bang there, whoops. But, because we're doing it live, that means I can and refresh. Whop! Hi from Rust! Woo! It's working! Add a line at the top to bring the standard library's file system module into scope. Code for reading contents of file to a string should look familiar. Used in chapter 12 when we read the contents of file for our IO project in listing 12.4. Alright. Yep. Then we format to add file's contents body. To ensure valid HTTP response, we add content length header, which is set to the size of our response body. Okay, it's the size of hello to HTML. Yep, run this code with cargo 1. Yep, just see it rendered. We did, yay. Currently, we're ignoring the request data and buffer and just sending back contents of the HTML file unconditionally. Means if you try requesting something, something else in your browser, you'll still get back the same HTML response. Very limited, and it's not what most web servers do. We want to customize our responses depending on the request and only send back the HTML file for a well-formed request to slash. Okay, let's. Alright, so validating the request and selectively responding. Right now, our web server will return the HTML in the file no matter what the client requested. Let's add functionality to check that the browser is requesting slash before returning the HTML file and return an error if the browser requests anything else. Okay. Yeah, let get equals b get slash http slash 1.1 back r back n. Alright, and that just reads, the b there just puts it into like an array of bytes. Okay. If buffer starts with get, now we can Alright. Yep. Now that'll look specifically get, like, this'll just get the home page and anything else just won't respond right now. Whoops. I should, Refer to tabs. Is there... I wish there was like a way to I guess Rust automatically starts it with spaces. I would prefer tabs, but oh well. Right, so now we've got that, and then we're gonna have an else. So now we can like put a 404 here or something, but yeah. First, we hardcode the data responding to the slash request into the get variable. As we're reading raw bytes into the buffer, yeah, transform get into a byte string by adding b at the start of content data, yep. Yep. If it doesn't, yep. Yeah, we've received a well-performed request, yep. Success case will handle an if that returns contents, alright. If the buffer does not start with bytes and get, it means we receive some other request. Add code to else block in a moment. Alright. So yeah, now if I save this and run and then text HTML. Hey, it isn't working, didn't send any data, yep. Control C, yep. Alright. Yay! Yep, now let's add code in listing 27 to the else to return a 404. So let status line equals HTTP 11404 not found. Let contents equals file system read to string 44 HTML. Unwrap and let response equals format back r back n content length dumb r back n but dumb status line contents len contents then stream write fonts as bytes unwrap stream flush unwrap. Wait, no, I put that on the wrong part. There. Okay. Response to status line with 404 recent phrase not found. Yep. That means we should make a new page. So, file 44 HTML. Doc type HTML. HTML. Lang equals yen. Head. Meta char set equals UTF-8 and title swap, then in the body one oops nope, oh, that's all the star 3. Yeah, the file you're looking for doesn't seem to exist. Alright. Yay! Yep, so now I can run this again. Okay, so... forward, yep. Alright, yay! That works. Control C. Close. There. Alright, so... yeah, now there's a lot of repetition, so they're both reading files and writing contents of the files to the stream. Yep, only differences are status line and the file name, so let's split them out. So basically what we're gonna do is, let status line file name if buffer starts with get HTTP 1.1 200 OK. Oh, I forgot to quote that. Ba ba da ba ba ba. And hello HTML. And else HTTP 1.144 not found. Oh, found 404 HTML. All right. And but then basically we can just copy all of that out. So I was gonna have something like this. So actually we're gonna always have something like this. So ba ba da ba 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 da ba. Then let me put that back. Then this will just go to file name there. Woo! Okay. Nice, nice, nice. Yep, that should all be undone there. But hey, hello, Punch Bunny. I am writing a web server. Yep. If and else only return the appropriate values for the status line and file name and tuple. Then use destructuring to assign these two values to status line and file name using pattern and let. Yep. Check voice chat and Alicia's server. Oh yes, I saw this earlier. Oh god. Oh, it's so good. It's so good. For those of y'all who don't know what I'm talking about, it's just so good. Oh boy, yeah. It's so bad. I saw this earlier. It is. I love cursed macro shit. I love how like so many languages just let you use macros to like just commit complete crimes. It's so good. It's so good. It's so good. These memes are the only good part I've seen of C macros, yeah. I love chaos. I love chaos. I just like chaos. You know, like, if you're not doing, like, the most ridiculous impractical stuff with your code, then what the hell are you doing? Alright, so, previously duped code is now outside of the if and else blocks and uses the status line and file name vars. Makes it easier to see a difference between the two cases and means we only have one place to update the code if we want to change how the file reading and response writing work. Behavior of the code listing in listing 29 will be the same as that in listing 28. Awesome! We now have a simple web server and approximately 40 lines of Rust code that responds to one request with a page of content, responds to all other requests with a 404. Currently, our server runs in a single thread, meaning it can only serve one request at a time. Let's examine how that can be a problem by simulating some slow requests. Then we'll fix it so our server can handle multiple requests at once. Alright. I will have like another break in a few minutes. Alright, so right now the server will process each request in turn, meaning it won't process a second connection until the first is finished. If the server receives more and more requests, this serial execution would be less and less optimal. If the server receives a request that takes a long time to process, subsequent requests will have to wait until the long request is finished, even if the new request can be processed quickly. We'll need to fix this, but first let's look at the problem in action. Alright, time to simulate stuff. Alright, so so we're gonna need to take in like standard thread and time duration. Okay. So, use standard thread, use standard time duration. Alright, so now we're gonna do, so now we're gonna put another else if buffer starts with sleep, and then we're gonna let sleep equals the get plus sleep HTTP 11 back n. And this should be thread sleep duration from x5 up, then HTTP 1.1 200 in HTTP 1.1 200. Okay, hello. .html. Lowercase. There. Better. Alright, so now, if we run this, sleep. Stop. Fucked up, because you don't want that bracket there. Run again. Running. Yep. For a second, why? Doing something wrong? Oh, now it's taking a bit. Okay, 1, 2, boom. All right, that's better. Sleep. All right. Yep. So, code's a bit messy, good enough for simulation purposes. Create a second step. Yep. Real libraries handle the recognition of multiple requests in a much less verbose way. Yep. Right. Yep. So now that takes a while. Yeah. Multiple ways we can change how our web server works to avoid having more requests back up behind a slow request. The one we'll implement is a thread pool. I'm gonna go to that in just a minute. I'll be right back. beep, 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 beep. Okay. So, a thread pool is a group of spawn threads that are waiting and ready to handle a task. When the program receives a new task, it assigns one of the threads in the pool to the task. That thread will process the task. The remaining threads in the pool are available to handle any other tasks that come in while the first thread is processing. When the first thread is done processing its task, it's returned to the pool of idle threads ready to handle a new task. A thread pool allows you to process connections concurrently, increasing the throughput of your server. We'll limit the number of threads in the pool to a small number to protect us from DOS attacks. Yep. We got a program create a new thread for each request as it came in. Someone making 10 million requests to our server could create havoc by using up all our server's resources and grinding the processing of requests to a halt. Rather than spawning unlimited threads, we'll have a fixed number of threads waiting in the pool. As the requests come in, they'll be sent to the pool for processing. The pool will maintain a queue of incoming requests. Each of the requests in the pool will pop off a request from this queue, handle the request, then ask the queue for another. This design we can process n requests concurrently or n's the number of threads. If each thread is responding to a long-running request, subsequent requests can still back up in the queue, but we've increased the number of long-running requests we can handle before reaching that point. This technique is just one of many ways to improve the throughput of a web server. Other options you might explore are the fork join model and the single-thread async IO model. If you're interested in this topic, you can read more about other solutions and try to implement them in Rust. The low-level language like Rust, all of these options are possible. Before we begin implementing a thread pool, let's talk about what using the pool should look like. When you're trying to design code, writing the client interface first can help guide your design. Write the API of the code so it's structured in the way you want to call it, then implement the functionality within that structure rather than implementing the functionality and then designing the public API. Similar to how we use TDD in the project in Chapter 12, we use a compiler-driven development here. We'll write the code that calls the functions we want, and then we'll look at errors from the compiler to determine what we should change next to get the code to work. Okay, that's interesting. Alright, so. Yep, code structure. If we could spawn a thread for each request, let's explore how our code might look if it did create a new thread. As we mentioned earlier, this isn't our final plan due to the problems with potentially spawning an unlimited number of threads, but it is a starting point. In 2011 shows the changes to make the main to spawn a new thread to handle each stream within the for loop. Okay, bad idea, but we could just like do a thread spawn around it there. Yeah, that would just be like very easy to exploit. As you learned in Chapter 16, thread spawn will create a new thread and then run the code in the closure in the new thread. If you run this code and load /sleep in your browser, then slash into more browser tabs, you'll indeed see the request to / don't have to wait for /sleep to finish, but as we mentioned, this will eventually overwhelm the system because you'd be making new threads without any limit. So, let's make some finite threads. Okay. What we want to do instead is want our thread pool to work in a similar, familiar way, so switching from threads to thread pool doesn't require large changes to the code that uses our API. Right, so we're going to want something like let pool equals thread pool new for. Then we'll want a pool execute handle, yep, and then we'll put in handle connection. There. Now, of course, thread pool doesn't exist yet. We've got to make it. So, yep. Then in the for loop, pool execute is a similar interface as thread spawn. It takes a closure to the pool, should run for each stream. You need to implement pool execute, so it takes the closure and gives it to a thread in the pool to run. This code won't yet compile, but we'll try so the compiler can guide us on how to fix it. Thread pool new doesn't exist. We've got our red squigglies there. Alright, so let's make a thread pool. Independent of the kind of work our web server is doing, so let's switch the hello crate from binary crate to a lib crate. After we change to a lib crate, we could also use the separate thread pool library for any work we want to do using a thread pool, not just for serving web requests. Okay, so that means lib.rs, boom. Okay, so pub struct thread pool. Yep. then we need to make a... Right, then we need to make a new folder. Bin. That's where main RS is gonna go. Move. Da, ba. Alright, so. This. Yep. Alright. Doing so will make the library crate and the primary key in the hello. We can still run the binary and source main RS using cargo run. After moving main RS, edit it to bring the library crate in and bring thread pool into scope. Yep, so use lemonette thread pool. Yay! Now, alright, so we need a new for that. Alright. Thread pool. A new count. U32 should not have a negative count. Yep. To thread pool. Or we should to do. There. Do in. Close that. We can hide that. Okay, yeah. Oh, also gotta make this pub. Alright, yep, and then we should do pub fun execute. Yep. Then like make a name for it, so connection fun to do. And alright, so all that is good. This just doesn't do anything. Actually. Oh. Actually, we might need to. Or no, we'll figure out that typing in a bit, but yeah. So, yep. Oh, U size, okay. Makes sense. And we're just gonna thread pool. Yeah, we're gonna have like, yeah, okay. Starting to have ideas, so yeah. Then we need execute, yep. Yep, creating similar. Yep, recall from creating a similar interface for a finite number of threads, yep. Start our pool should have an interface similar to thread spawn. In addition, we'll implement execute so it takes the closure it's given and gives it to an idle thread pool run, yep. Define execute method on thread pool to take a closure as a parameter, yep. Yep. We can take closures as parameters with 3 different traits, fun, fun mute, and fun once. Need to decide which kind of closure we're going to use here. No, we'll end up doing something similar to the standard lib thread spawn. So we can look. So, what is, thread spawn, B. So that is, yes, so that is fun once, T, okay, yep. Alright, so yeah, we're basically just gonna take this, yep. F-type parameter is the one we're concerned with here. T-type parameters are related to return value and we're not concerned, so yeah. Yep, so this is gonna be F. And once. There. Something like that. Yep. Oh yeah, we also need to send we're gonna have plus send plus prime static. Okay. And that's getting a bit long, so we could like just split it out like that, yeah. Where F wants plus send plus static. Something like that, maybe. Right. There. Yep. I can get rid of that, yep. Oh, thank you for the hydrate, Nikki. And a posture check. Yeah. Yeah. Deep. Weren't concerned with here. T parameters related to return, not concerned. Yep. Fun uses fun once, is trait bound on F. This is probably what we want as well. Yep. Yep. Confident that fun once is trait we want to use because thread for running request will only execute that request closure one time. Oh, message once and fun once. Yeah. F-type parameter also has trait bound send and lifetime bound prime static, which are useful. Yep. Need send to transfer the closure from one thread to another in prime static because we don't know how long the thread will take to execute. Yep. So it'll. Yep. Oh yeah. We also need to and self. Oh, they do that. Okay. Yep. And then I could also like just that. Yeah, there. Then, yeah, then we'll just keep to do there for, yeah. We don't even need that, but yeah. To do is helpful because I believe it will just like, yeah, just panic. Yep. Yeah. It'll just panic on compile. While to-do conveys intent of implementing later, message is not yet implemented yet. Its message is not implemented yet. Some IDs will mark to-dos, yep. Just looking to have your code type check, you can just use to-do, yep. Okay. Yep. Then, yep. Return type can be omitted. Even if we have no parameters, still need parentheses. Yep. Then simplest implementation of execute does nothing but trying only to make our code compile. So yeah. Now, I can yay. Yep, and that'll crash just because it's yep, that'll just panic on call. Yep, at not yet implemented. Boom. Yeah, that's fine. Yep. Yeah, because we aren't actually calling it. Yep. The thing you might hear about languages with strict compilers such as Haskell and Rust is if the code compiles it works, but this is not universally true. Yep, our project compiles but does nothing. If we're building a real complete project, this would be a good time to start writing unit tests. Yep, yeah. Yeah, just because something has a good type system doesn't mean that it is comprehensive. Yeah, completeness does not come purely through types. Right, so we aren't doing anything with new and execute, so let's implement them. Ooh, some doc strings. New size is the number of threads in the pool. Mechanics. Yep. I just hit a keystroke from my other keyboard. Whoops. New function will panic if size is 0. Yep. Now we can assert size greater than O. There. That's good. Yeah. Alright. Add some docs to our thread pool with doc comments. Yay! All good doc practices by adding a section that calls out situations which can cause panic. Yep, so now I could, Press, you have one for... Yeah, Cargo doc, open. Oh, oh right, I have HTML files bound to Atom. Ah! I forgot I did that. I should probably, like, let him softly. Hello, Sunrose! It's great to see ya! I am doing the final project in the Rust book right now. Hope you're doing, yeah, hope you're having a good time. Yeah, Beep. Okay. Yep. Alright, so, yep, thread pools, dot comments, yep. Good, like, property. Yeah, there. Now that would open it up in my browser, so... Cargo, doc, open, ba-ba-da-ba, yay! Currently uploading a redacted YouTube. Oof, stream keeps buffering. Ooh, I'm not like, yeah, yeah, that might be your side. Yeah, I'm not getting any, like, warnings about, like, encoding issues or dropped frames, so, yeah, not sure what's up. Yeah, turned off low latency for now, yeah. Right. I messed up this. Am I turning to? Oh. Doesn't actually seem to make the latency any higher, yeah. Fix the buffering, yay! Yeah, alright, so back to this. So yeah, now I've got docs! Yay! Yep, got that. Yeah. Just doing some, like, stuff with one of my stim toys to get it to reset there. Yeah. Yep, so now we've got docs! Woohoo! Does feel like it, like, I could have sworn, like, Rust Analyzer had, like, a thing for, like, documentation. Oh well. Alright. Yep. Instead of adding assert macros we've done here could make new return a result. We've decided trying to create a thread pool without any threads should be an unrecoverable error because you can't do anything with it. Yep. Feeling ambitious, try to write a version of new following signature for results. Yep. Alright, creating space to store the threads. Now that we have a way to know we have a valid number of threads to store in the pool, we can create those threads and store them to the thread pool struct before returning it. How do we store a thread? Let's take another look at the thread spawn feature. Yeah. Create signatures. Yeah, we've got like fun once, and also send. Okay. Thread spawn function returns a join handle where T is the type the closure returns. Let's try using join handle 2 and see what happens. In our case, closures we're passing to the thread pool will handle the connection and not return anything, so T will just be unit type. Yep. Yeah, we're just gonna use standard thread. Yep, so gonna threads spec thread join handle there. Then you are, yep, this is UB, so yeah, so there's gonna be an issue here. You disable... I did disable it a few streams ago, yeah. Or, I disabled, like, the hover one, but, like, there's also, like, the, there also, like, having, like, a button to open it up in, like, browser or such, but yeah. Not that important, yeah, so now we can, yep, do that then. Let mute threads equals vec with capacity size, or don't care in O size. Create your threads here. And thread pool threads there. Right. Yay. If this is angry because it's not mutable, yeah. Right, yep. Yeah, so, yep, brought standard thread scope in the library crate, yeah, because we're using join handle, yeah. Once valid size received, our thread pool creates a new vector that can hold size items. We haven't used with capacity in this book yet, which performs the same task as vecnu, but with an important difference. It pre-allocates, yay! Because we know we need to store size elements in the vector, doing this allocation up front is slightly more efficient than using vecnu, which resizes itself as elements are inserted. When you run cargo check again, you'll get a few more warnings, but it should be fine. Just like, this doesn't do what, yeah, this doesn't do what we want it to because, like, we aren't actually making the threads, yeah. Worker struct responsible for sending code from thread pool to a thread, okay, yeah. We left a comment in the for loop in 2014 regarding the creation of threads. Here we'll look at how we actually create threads. Standard library provides thread spawn as a way to create, and thread spawn expects to get some code the thread should run as soon as the thread's created. However, in our case we want to create the threads and have them wait for code that'll send later. Standard lib's implementation doesn't include any way to do that. We'll have to do it by hand, okay. Yep, so new data structure, okay, yep, between the thread pool and the threads. Call this data structure worker, which is common to term in pooling impulse. Think of people working in the kitchen in a restaurant. Workers wait until orders come in from customers and then they're responsible for taking those orders and filling them, but yeah. So instead of storing a vector of join handles, we'll store instances of the worker struct. Each worker will store a single join handle instance, so yeah, we're gonna have a struct worker thread join handle, but so this is instead going to be a vec worker. Lowercase t. Yay. Yep. There. Okay. Yep, instead of storing a vector join handles, restore instances of worker. Each worker will store a single join handle. We'll implement a method on worker that takes a closure of code to run and send it to the already running thread for execution. We'll also give each worker an ID so we can distinguish between the different workers in the pool when logging or debugging, okay. Yep. So ID, size. Alright, then we're gonna want, impl worker. Yep. Then new worker. Or no, this is gonna be ID. ID. New size. Worker. ID. Then we'll just do like an empty thread there, but yeah. That's not quite right, but yeah. Yep, now we're just gonna do, yep. workers. Just, yeah, we're going to call these workers. Yep, then for ID. Yep, then workers, push, worker, new ID. Yep. And yeah, we're gonna have thread with, yep. We're gonna have join handles, yep. Then gonna let thread equals thread spawn da da and da. Then we're just gonna have thread. And hell, we can just simplify that to IDE thread. Woo! Now we might want to do something more complex here, but we'll figure that out yet. Change the name of the field on thread pool from threads to workers, because now it's holding worker instances instead of join handles. Counter in the for loop is an argument to worker new, and we store each new worker in the vector named workers. Yeah. Journal code, like server and source bin main RS, doesn't need to know, so we can just keep it all private. Yep. Well, I might want to like just put this down here. Below all the public stuff. Alright. To make the worker struct in its new function private, worker new uses the ID we give it and stores a join handle that's created by spawning a new thread using an empty closure. Yep. This code will compile and store the number of worker instances specified, but we're still not processing the closure that we get and execute. Let's do that. Channel time, channel time, channel time. Now we'll tackle the problem that the closures given to thread spawn do absolutely nothing. Currently, we get the closure we want to execute in the execute method, but we need to give thread spawn a closure to run when we create each worker during the creation of the thread pool. We want the worker structs that we just created to fetch code to run from a queue held in the thread pool and send that code to its thread to run. In chapter 16, we learned about channels, a way to communicate between two threads that'd be perfect for this. We'll use a channel to function as the queue, and execute will send a job from the thread pool to the worker instances, which will send the job to its thread. Here's. Alright, thread pool will create a channel, hold on to the sending side. Each worker will hold on to the receiving side. Is that? I could have sworn that channels are, yeah. Oh, there is a multi-producer single consumer one. Okay. So yeah. We're gonna use that, yep. We'll create a new job struct that'll hold the closure we want to send down to the channel. So we're gonna need to use standard sync multi-producer single consumer. Yep. Now you're gonna want a sender MSPC sender job. We're gonna make, yep, a struct job. MPSC. Yep. And now we're gonna do stuff with it. Yeah, so we're gonna let sender receiver equals MPSC channel. Then we're gonna send that receiver here, then no, sender. And the workers should for MPSC receiver job. Yep, so then you're gonna want a new an ID and a job. Oh yeah. Receiver, yes. The receiver job ID thread receiver. consume. Then, copy? No. That's borrowing. Yeah, that's a lot of illegal borrowing, but yeah, we'll figure that out in a bit. Wait, no, are we gonna, like, use... We're probably gonna use, like, probably gonna use Arc or something. So yeah. Create a new channel, have the pool hold the sending end. This will compile, it's still with warnings, yep. Let's pass the receiving end of the channel into each worker's thread pool creates, yeah. Yeah, this is like where I'm at with, like, the borrow stuff. That's an issue, yeah. Ah. So yeah, now we've got yep. Yeah. Create a new channel, have pool hold the sending end, yep. We now want to use the receiving end of the thread work responsible reference receiver. Yep. Code listing 2017 won't compile quite yet, but yeah. We've made some small, straightforward changes past the receiving end, and then borrow time. Oh, perfect timing when the borrow. Yeah, Cynthia's team when the borrow checker's causing issues. Yep. You'll call from chapter 16 channel input that Rust provides is MPSC. Yep. Multi-producer single consumer. Yep. Means you can't just clone the consuming end of the channel to fix this code. Even if we could, that's not the technique we would want to use. Instead, we want to distribute the jobs across threads by sharing a single receiver among all the workers. Ooh. Hydrate, thank you. Great. Yeah, so multi-producer. Yep. Yeah, so basically it's time to arc mutex, yeah. Alright, so, yeah, Arc and Mutex at the same time. Yeah, so... Yep. Yeah, this means can't just clone the consuming end channel to fix this code. Even if we could, not the technique yet. We want to distribute the jobs across threads by sharing a single receiver, yep. So, that's mutating! So thread needs a safe way to share and modify receiver, otherwise race conditions. So yeah, we're gonna, arc MPSC mutex, yeah, mutex, MPSC, there. And then, that means, yep, so that means receiver is gonna be, yep, receiver, let receiver equals arc, new, mutex, new, receiver. Then you instead will be an arc mutex you're an arc mutex. That's a hell of a type, so we could like then we have to arc clone and receiver there. Yay! Now I could like type alias like the arc mutex receiver job, but yeah, we'll see. Yeah, just arc mutex MPSC, yeah, gay. Hello Alicia, wonderful to see ya. Hope you're doing a good time. Yeah, hope you're having a good time. Yeah. Yeah, alright, so, yep. So we've got all this, yep. Arc clone. Arc new, mutex, new receiver, yep. Then we've got all this down here, yep. In threadpool new, we put receiving end of the channel in an arc and a mutex. For each new worker, we clone the arc to bump the reference count so the workers can share ownership, yep. So it compiles, but still does nothing. So, implementing the execute method, yep. Yeah, no, job's not going to be structured, it's going to be a type. Job equals box in fun once plus send plus prime static doom. Alright. And now in this we're gonna let job equal box new f, then self sender send job unwrap. Yeah. Now we're gonna have to do more stuff, so after creating a new job instance using the closure we get an execute, we send that job down the sending end of the channel. Yep. Calling unwrap on send for the case sending fails, like meaning receiving end stops receiving new messages. The moment we can't stop our threads from executing, our threads continue executing as long as the pool exists. The reason we use unwrap is that we know the failure case won't happen, but the compiler doesn't know that. Not quite done yet. In the worker, our closure being passed to thread spawn still only references the receiving end of the channel. Instead, we need the closure to loop forever, asking the receiving end of the channel for a job and running the job when it gets one. Yep. Let's make these changes. Okay, so yeah, now, this instead is gonna be move, loop, let job equals receiver, lock, unwrap, recv, unwrap, lots of unwrapping, println, worker, got a job executing ID and job. Why are you angry? Moving? Wait, yeah, Good? That should be fine, yeah. Alright, you call lock on the receiver. Yep, so first we've got to lock the receiver, then unwrap that. Then receive, then unwrap that. Just because we should theoretically in like production do like something more careful, but it doesn't really matter. Alright. Yay, yep. In this situation, calling unwrap to have this thread panic's correct action to take, yep. Feel free to change this unwrap to an unspect. That, yep, with an error message that's meaningful to you, yeah. Call recv to receive a job from the channel. A final unwrap moves past any errors here as well, which might occur if the thread holding the sending side of the channel is shut down. Similar to how send method returns error if the receiving side shuts down. Call to recv blocks. Yeah, block, so if there's no job yet, current thread will wait until a job becomes available. Mutex ensures only one worker thread at a time is trying to request a job. With the input of this trick, our thread pool is in a working state. Yep. Yeah, there are going to be some concerning things there, just don't worry about them, okay. Over here. Alright. Running, boom. Alright, then... Sleep, boom. Yay. Boom. Yay. Things are working, woohoo. Alright, that is a web server. Like, it's working, yeah. Well, kinda, but yeah. Thus, we now have a thread pool that executes connections asynchronously. There are never more than 4 threads created, so our system won't get overloaded if the server receives a lot of requests. If we make a request to last sleep, the server will be able to serve other requests by having another thread run them. Yep. If you open last sleep in multiple windows simultaneously, they might load one at a time in 5-second intervals. Some web browsers execute multiple instances of the same request sequentially for caching reasons. This limitation is not caused by our web server, alright? After learning about the while let loop in chapter 18, you might be wondering why I didn't write the worker thread as code as shown in listing 2021, yep. Yeah, that's like, we've got like the while let. Yeah. Code compiles and runs, but doesn't result in the desired threading behavior. Slow requests will still cause the others to wait to be processed because Mutex has no public unlock method because the ownership of the lock is based on the lifetime of the Mutex card that the lock method returns. At compile time, the borrow checker can then enforce the rule that a resource guarded by Mutex cannot be accessed unless we hold the lock. But this implementation can also result in the lock being held longer than intended if we don't think carefully about the lifetime. Yep, so, yeah, code listing 2020, the use let job equals receiver lock on wrap directly on wrap works because with let, any temporary values used in the expression on the right hand side of the equal sign are immediately dropped when the let statement ends. However, while let and if let and match does not drop temporary values until the end of the associated block. In listing 2021, the lock remains held for the duration of the call to job, meaning other workers can't receive jobs. That's not good. Alright, and lastly, let's do some graceful shutdown and cleanup. Code used in listing 2020 is responding to requests async through the use of thread pool. Yep. Get some warnings about the worker's ID and thread that we're not using in a direct way that reminds us we're not cleaning up anything. When you use the less elegant Control-C method to halt the main thread, all other threads are stopped immediately as well, even if they're in the middle of serving a request. Now implement the drop trait to call join on each of the threads in the pool so they can finish their request they're working on. So yeah, over here. Yeah, so that means we're gonna impl drop for thread pool drop. We're just gonna so for worker in and mute self workers println shutting down worker D worker thread join unwrap. And this is an issue because it cannot move out of worker thread, which is behind a mutable ref, because it has type join handle, which is not copy. Okay, first loop through the thread visuals and mute for this because self is mutable. Mutable. And we also need to be able to mutate worker. For each worker, we print a message saying the particular worker is shutting down. We call join. Called join fails, we use unwrap to make Rust panic and go into an ungraceful shutdown. Here's the error we get. Yep, that's just a move. Yep, not copy. Can't call join because we only have a mutable borrow of each worker, and join takes ownership of its arg. To solve this issue, we need to move the thread out of the worker instance that owns thread so join can consume the thread. Did this in listing 1715. Yep. Worker holds an option thread join handle instead. Yep. Yeah, we're going to option thread join handle, and then we're just be some thread. You know, hell, I could do that. But there, that's good. Yeah, then take. Then gonna if let some thread equals and thread there. Good. I think we're good. I think we're good. Yeah. Yep. Option thread join handle. Yep. Then we're gonna they did that sum there. I just did it in the let thread there, just because it looks a bit cleaner there. Yep. Then if let sum. Yep. Worker thread take thread join unwrap. Yay. Alright, then with all the changes we've made, our code compiles without any warnings, but the code doesn't function the way we want it to. Yep. In logic closures. Yep. At the moment we call join, but that won't shut down the threads because they loop forever. Try to drop a thread pool with our current input. The main thread will block forever, waiting for the first thread to finish. Fix this problem, we'll modify the thread so they listen for either a job. Alright, yeah, so in a message, new job, terminate. Then this is going to be a message, not job. Message. Yep. Message. Then if let new job message new job equals message then job there. Yeah, feels right. Yeah, then this will have to be, yeah, this will be message new job. Oh, they're doing a match. Okay. Oh yeah, because we're still in, yeah, should match message message new job to and job and message terminate to println worker was to terminate ID break. Okay, then yep, should be good. Yep, need to change job to message in places. Yep. Alright, with these changes, code will compile and continue for function in the same way as it did after listening to 2020, but we'll get a warning because we aren't creating any messages to terminate variety, so we gotta do that. Capital N there. Then, yep, then we've gotta, and drop, yep. Println sending terminate message to all workers, or don't care in and self workers, self sender send message terminate unwrap there. Then println shutting down all workers. There. Oh shit. Oh shit, playlist is done. Well, luckily I'm pretty much done. So yeah. Yep, iterating over workers twice. Yep, once terminate and then, yep, then call join. Try to send a message and join immediately. We couldn't guarantee worker in the current iteration would be the one to get the message. So yeah. Better understand why I need 2 loops. Imagine a scenario with 2 workers. Yep, basically race conditions, deadlocks. Yeah, bad stuff. Yep, terminate in 1 loop, then iterate through again, but yeah. Yep. See this code in action, yep. So this will let, yep. Few things here, yeah. I'll just longer, but yeah. Yeah. Yep. Oh, yep. And, alright, so take 2 and println shutting down semicolon run. Refresh. Alright, got a job, then let's Sleep. Yeah. Yay! Complete. Alright. Yeah, that works perfectly, yay. Want a real-world web server to shut down after serving only 2 requests? Yep, just demonstration, yep. Take is defined in iterator, limits iteration to first 2 items, yep. Yep, got something like that. Yep, different ordering, of course, yep. Notice one interesting aspect. Threadpool sent the terminate messages down the channel before any worker received. We tried to join worker O. Worker O had not yet received the terminate, so main thread blocked waiting for worker O to finish. Each of the workers received the termination messages. When worker O finished, main thread waited for the rest of the workers to finish. Yep. At that point, they'd all received the termination message and were able to shut down. Yay! Congrats! We've now completed our project. We have a basic web server that uses a thread pool to respond asynchronously. We're able to perform a graceful shutdown of the server, which cleans up all the threads in the pool. Yep, all this stuff. We could do more here if you want to continue enhancing. Here's some ideas like docs to thread pool and public methods, add tests for functionality, changes to unwrap for more unwrap to more robust error handling, thread pool to perform some task other than serving web requests, find a thread pool crate on Critsound, implement a simpler web server using that crate, then compare its API and robustness to the thread pool we implemented. Summary. Well done! You've made it to the end of the book. We want to thank you for joining us on this tour of Rust. You're now ready to implement your own Rust projects and help with other people's projects. Keep in mind that there's a welcome community of other Rustaceans who would love to help you with any challenges you encounter on your Rust journey. I am finished. And I am so proud of myself. Yeah. There's, like, theoretically more, but, like, that's just appendix. There's a bunch of other, like, documentation stuff I could do at some point. But yeah, I am really happy with this. Let's switch back over to just chatting. Yeah, hate how it, like, kills all chat. I should figure out how to make it not. Yeah. I am so fucking happy with this. I am really proud of myself for just getting through the book. Yeah. Like, I have just gone through, like, the entirety of, like, the Rust book, and I am really, really proud of myself. Yeah. I'm just, like, so happy. I'm really happy with, like, all of this, like, and I definitely want to, like, use some, I want to use Rust for some, like, actual, like, bona fide programming projects. I would be really excited to do that. So yeah, I'm definitely gonna do that later down the line. Oh boy, I'm gonna need to figure out what to do for my Friday streams from now on. I like a few ideas of things I could do, but yeah. I should also, find someone to go raid now, because, like, I'm done. Like, don't have anything else, like, really to do in the book. So yeah, you know, oh, Boki's live. Yeah, I should go over there. So we're gonna go soft Robo Raid. Actually, you know what? We're gonna go with Rusty Robo Raid. Oh shit, I just realized I didn't have Ferris up at all this stream in the last one. I'm so sorry, but yeah, gonna go with Rusty Robo Raid. We're gonna raid Boki Pixel Art. Thank you all so very much for watching, hanging out, joining in. This has been really fun, really nice. I am so happy with everything I've gotten done, and in the future, I'm definitely gonna be using this for more. But yeah, when we get over to Boki's page, please do not forget to drop them a follow, because they are super cool and neat and awesome. But yeah, tomorrow, what am I gonna do again? I made this, right, yeah! I'm gonna be playing Code 7, a cool, like, story-focused hacking game that I, like, found, like, ages and ages ago, but I haven't really gotten around to playing. But yeah, hope you all come hang out and tune in for that. But yeah, for now, I am gonna send y'all on over to Boki. How about we get this raid started in 5, 4, 3, 2, 1. See you soon.